Alright, welcome to Meteorology 101. I've got a lot of tornado warnings out there. So anybody wants to follow along, we're going to chase these storms out. Right now I'm going to pull the surface chart. Alright, I got surface data just came up. So look at that rotation right there in Nebraska. We got 35 to 40 knot winds. This is sustained observed winds. So we got a pretty strong system coming through Nebraska right now. Plenty of tornado warnings. And we'll go back to we'll go to the radar in just a second. I'm going to pull up this surface chart, complete this chart real quick. We can see where the low pressure system is, what's causing this, and then put our isotherms on here so we can see where the thermal ridge is. If there's a thermal ridge around this low, going into the center of this low, then we can pretty much pinpoint where our severe weather is going to be. So we do have a thermal ridge to the east of this low. Winds are out of the south, about 25 knots. There's our thermal ridge up into Iowa and pushing up into Minnesota. So as this thing pushes east, we can look for pretty much significant weather, mainly all the way through Iowa. We got 59-degree dew points, and there's a 56, 59, 47. So as this pushes east, we got the dew points to give us the instability we need to create tornadoes. So let's go. I'm just going to throw some fronts on here real quick associated with this. We should see a front coming down out of that trough. These are computer generated, so we've got a cold front there, and our warm front's pushing north. It already shows that north of Iowa. We got our thermal ridge, all the warm air right behind that warm front. That's our warm sector. So as this cold air comes pushing through and lifts that warm, moist air, then that's where we'll get our squall line and any significant weather. So what we'd have to do is pull the 850 millibar chart and look at this low pressure system, try to find the upper front. Once we did that, we could see the slope of that front, how steep that is. And if it's more steep, we'll have a shallow area of thunderstorms right in front of that, ahead of that front. And if it's shallow, then you'll have most of your thunderstorms and severe weather behind that front. So right now, let's go pull the local radar for eastern Nebraska. So you can see our squall line here. That's pushing through pretty good. We got plenty of tornado warnings and tornado watches going on. We got squall line, squall watches to the west. That's where the snow squalls were that dropped visibility pretty much to nothing. With the winds blowing, we got reported 80 knot winds. Let me pause this for a second. Get to let's go back to the last screen. This is the first loop screen of the radar loop. So 55 knot winds, 80 knot winds reported, 70, 60, 80. So any of this with just significant winds in that area. We got 55, 60 knot. These are all pretty current. And then we could go to the latest shot. Now we can see where there's just tornado warning after tornado warning. Most of these, some of these are reported on the ground. You can see these areas that are tornadoes reported on the ground by the fire department. This is reported by law enforcement. This one's reported by the fire department. Confirmed tornadoes on the ground. All these red are tornado warnings. Most of this is probably rotation indicated by radar. If I click on one of those, I can see the details of this thing. So this has been canceled, but there's still a tornado watch in effect, I think until 8 p.m. So we got tornadic thunderstorm, which prompted a warning, has moved out of the warning area. So let's go back. The ones I want to watch is where there's actual tornadoes being reported on the ground. So we're going to look at this cell up here. It looks like most of it's died out. Let's go ahead and play the loop. So we had a pretty strong reflectivity right where that tornado was, and then that pushed out. But we still have a little bit of a curvature right there. But they just dropped that warning. Pretty much most of that's dying out. Looks like a lot of this is with the sun going down, it's losing its energy. But with this low pressure system, we go back here real quick. We got clear this out and put the pressure only. I want to see the center of that low. You can see the isobars on the surface chart, how tight they are. That's all of our significant winds. I mean, you're looking at 20 to 40, 45 to 45 knot wind sustained around this low pressure system. We have a 993 millibar low, which is a pretty good low. It's not the worst we've seen, but anything 1,013 millibars is your standard atmosphere. Anything below that is considered low pressure. So we're starting to deepen. We'll pull another update in a little bit and see if that does deepen. But let's go back to the radar again. We're going to track mostly into this radar. I want to see real quick. This is eastern Nebraska, so we're going to look at real quick. We're going to pull a model. And this is the HRRR, the high resolution rapid refresh. We're going to look at the next few hours. That's a pretty strong squall line when it hits Iowa. Like we said, we had most of our higher dew points in Iowa, so we will look for significant weather pushing all the way through Iowa. Let's watch this for the next few hours. Like I said, you can see it all the way through Iowa, and then looks like a lot of that frontal system dies out, and then the significant weather pushes to the north into the Great Lakes region. But with this low, it looks like it steers pretty much northeast and then through central Minnesota. And you do have some significant weather from stretching right there from Minnesota all the way through Wisconsin and western Wisconsin. There's still some pretty good convection in those areas. So we'd have to pull... let's pull our convective chart. We'll look at our cape. Here's our cape right here. So let's see what we got. 200, 300 joules. Nothing really significant. 600 down in this area. Let's go back as we push through Iowa. 500 to 600. Yeah, pretty much 500 to 600. So most of that is look like it may just die out. We don't have the energy there. There we go with this one. This is where we are in eastern Nebraska. We're over 1,000 joules, so we do have the energy in that right there. So it looks like, based on the cape, a lot of that will die out. It looks like a pretty good chance from, like I said, from eastern Minnesota down through Wisconsin. I've seen about a 500 in there. So there's a slight chance for severe weather, maybe some severe storms. I don't know if we're going to have tornadoes in that area. We'll have to see what this system does as the sun goes down. It's most likely going to weaken because if it loses daytime heating. Let's get back to the radar. Alright, so as this pushes northeast, there's still some warnings that were being set. And then it just looks like it just weakens pretty much all the way through. So let's go. Let's do a cross section on this thing. I'm going to see about where that tornado was, what we had for. Get a smaller shot on that. Actually, you can't see that yet. I'll pull that back up. Alright, there's our cross section. This is pretty much elevated. We do have a little bit of a tilt, but there's really nothing at the lower levels. We got 50 dBZs over 20,000 feet, almost 30. So that is definitely a severe system, and could produce a tornado on the ground. We did get one report on that. Let's see what we got here. That was a tornado in Beamer, Cumming County, Nebraska, reported by the fire department. It was confirmed. Let me get back. So that one was this one right up here. Let me go right there. That one is confirmed on the ground. So let's go a couple screenshots up. Got a pretty significant line here to the south. If we pull that one, and we can see the elevation on that reflectivity. Pretty good tilt, real good tilt on that storm. Now we're getting into some higher reflectivities, and we got 60 dBZs up to 20,000 feet. That is definitely a severe storm. We actually got a higher reflectivity, pushing some hail. Those higher reflectivities most likely hail, unless you have a actual tornado on the ground throwing debris that high, which typically doesn't happen for throwing debris up to 20, 30,000 feet, except for that storm we had last Friday. That one actually did throw debris to 30,000 feet. All right, let's go ahead and play this loop. And get rid of just the tornado watches, anything that's not confirmed. Get rid of that. Alright, so we got another report on the latest screen right there. Power flashes from power lines reported by a storm chaser. It's 3 miles east-northeast of Lawton in Woodbury County, Iowa. So we're going to have to keep an eye on Iowa, because we got those dew points that are pretty high in that area. And like I said, as that low pressure system pushes northeast, we may see some pretty significant weather through Iowa. And being as flat as Iowa is too, that there's really no friction to slow the stuff down on the surface. So. I don't see anything on here. I'm trying to find out if looking at my chat here. Okay. get back to the radar real quick. Let's do there's a national radar. You can see the rotation on this storm. Let me get it's right there where that low pressure system is in Nebraska. Then you got wraparound moisture, cold air pushing down, catching up with that warm air, undercutting that warm air. It looks like this thing's already occluded. And you got some wraparound moisture, and that with that cold air being behind that low, then all the precipitation falling through that high pressure system, and that cold air is causing snow because it dropped the freezing level pretty low. So this up to the north, we got another system moving to the northeast. It looks like mixed snow and rain showers all through New York. There's a high pressure system off the coast. Looks like it pushing the warm moist air to the north. And we got ridging into the southeast. Still some couple places with some low ceilings. A lot of moisture being pumped out of the Gulf from this system, and then the low pressure system pushing up against that high, tighten that packing, that the pressure gradient, and causing those significant winds. Okay. Alright, let's go back to get on the radar real quick. Make sure we don't have nothing significant happening. We got play that out. Looks like that line just pretty much broke up. Most of the tornadoes were up to the north, right around the center of that low. Pretty strong winds with that pressure gradient from that low pressure system. Get to the last screen there. We can see thunderstorm wind damage by reported by an emergency manager. Winds blown out, windows blown out, and roof damage. We have a thunderstorm wind gusts of 70 miles per hour reported by a trained spotter. Residential building collapse by an emergency manager. That's Douglas County. We got an 80 miles per hour wind but reported by an emergency manager from the thunderstorm gust. There's another 80 mile per hour wind by a trained spotter. And a 75 mile per wind gust reported by thunderstorm wind gust reported by a fire department. So like I said, 60 to 70, pretty much 60 to 80 knots, 80 mile per hour winds all through that area behind this system. So we got another little cell building up to the south. Let's do a cross section on that real quick, see what we have. Pretty much nothing in the upper levels. Looks like most of it's elevated. We do have some higher reflectivities toward the surface. Let's go. What we could do is look at that thing close. Like I said, we got that elevation, but if we go up into the elevation of that radar. We change the degree of the radar. Now we can see that doesn't go up very high. Another thing we can do is pull our base velocity, and you don't see any rotation. So that's why they're not showing a tornado warning or a severe warning in that area. Also go, let me get to another panel here. We can go vertical integrated liquid. There's really nothing there at all. So if we're pushing vertical integrated liquid all the way to the top of this storm, then we can get some significant weather out of that, but we're not showing it. That's the storm relative velocity. Echo tops, we're not even showing anything on the echo tops. If you get echo tops up to 20, 30,000 feet, then you can look at that cell a little bit closer. Like, let's go up to 4 echo tops here. Let's see what we had for these tornadoes that were spotted. So you can see there's one 17,000 feet, 17,000 feet. We really didn't even show a lot of echo tops on the in that tornado area. Let's go vertical integrated liquid. What do we have? Pretty much nothing there either. Not too impressed with those, but there was this says power lines down across Highway 20. And the time is estimated by radar. It was 2231Z. It's about 4 o'clock, and then it's 3 miles east northeast of Lawton. It says tornado, and that was reported by a storm chaser. Reported by the fire department. And thunderstorm wind damage, 80 miles per hour. Back here to the got pretty significant right there. We hit a pretty good curvature in that echo right there. Let's go. We did have the vertical integrated liquid. That one was at 22 kilograms per meter squared. Let's go echo tops. Now we're starting to see some echo tops. We got 32,000 feet, so that one was pretty significant. Let's go change the radar site. Let's go over here into Iowa. Download the latest data on that. Non-thunderstorm wind damage reported. Tree down on a power line resulted in power outage, including traffic lights. That's in Polk County, Iowa, 1 mile south-southwest of Johnston. Okay. Let's go back to the base reflectivity now. We got some pretty strong echoes on this site. Let's go right here's an area we need to watch. We got some high reflectivities. Let me get to the latest screen there. Now we do a cross section on that. We try to pinpoint that. Sometimes it doesn't catch the right capture. Looks like we need to go south. I can always twist it too. Let's go see if we can catch it. Nothing there. We got some pretty good tilt there. There's our higher reflectivities, pushing about 18,000 feet or so. Right there at 60 dBz. Let's see where that went. I just lost it. Okay. All right, so when we see that angle, that tilt angle, that's pretty much kind of an indication of you got 50 dBZs up above 10,000 feet, you can get a severe thunderstorm. That's all you need for severe. Then you get 60 dBZs pushing up to 20,000 feet, you can go almost to a tornado at that point. Especially with this angle, we got that tilt, that's our updraft, and then we can start seeing a downdraft come back down, and then you can see that wrap around and start becoming a tornado forming on the radar. So that's what they're looking for. Anytime they see that rotation, actually go to the base velocity. The base velocity will show you the incoming and outgoing winds of the radar. So our radar is located right here to the east. So all of the hot colors, or I guess the cool colors, would be in toward the radar, and then all of the hot colors are out of the radar. So you could say those winds are pushing out, these are pushing in. So we definitely got rotation here. That's why they're showing these thunderstorm warnings. So if I click on one, I don't think you can see that. Let me do something here. Okay, so now I can click on those. We can see the warnings. Tornado warning remains in effect until 5 p.m. Central Time for Cass County, and it gives you the details. And then the source is a radar confirmed tornado. So radar confirmed tornado is rotation on the radar. You don't have to have somebody on the ground reporting that. Anytime the radar shows rotation like this, or any kind of gate-to-gate shear, which you got these pixels, they start pushing against each other, one going out from the radar, one coming in. You got a lot of gate-to-gate shear right there, then you can pretty much put your tornado warning out. So we can go to different elevations of angles of this radar, different degrees, and we can see how far up this extends. We can also, I can do a 3D volume scan on these warnings also. Once you start seeing these curvatures, that's another thing to look for any kind of rotation. You get that those winds blow around these areas and they start pushing in, and then that kind of clears that out on the outside edges and starts becoming, where you can indicate rotation. Let's do a 3D scan on this one real quick and see what we got. So we got 50 dBZs well above 20,000 feet. You can see the couple updrafts shooting up pretty high on that. Let me get I can break this down pretty good. Let me get. We're not picking up a lot of reflectivity in the lower levels though. Most of this stuff's elevated, so we could have definitely some pretty significant rotation in the upper levels, so it's not hitting the ground. So let's go with I got this other tool here I can pull. I can get rid of the higher reflectivities. Here's to show you the outline of the whole storm. If we go to the base reflectivity on this thing, like 10 dBZs, this could be anything from, when you get this high, you definitely got clouds in that area. So 10 dBZs is nothing. On the surface, you could have just ground clutter, and that will cause that. Now, but what we can see from it is we can see our overshooting tops. Once we hit the tropopause, when that updraft goes all the way up, it's just pushing almost 40,000 feet. It goes all the way up, hits that stable layer where the tropopause is at the top of the troposphere, then it will actually overshoot that just a little bit, and you can see we have overshooting tops. So we got a pretty significant storm here. Let's go. This is just one section of dBZ, like 5 to 10 dBZ, 10 to 20, 20 to 30, and as you can see, the higher reflectivities get into the center of the storm. Let me get this thing out of the way so you can see that now. So we go 40 to 50. Once we hit the 50 dBZ mark, that's where, like I said, anything over 10,000 feet could be a severe thunderstorm. It's possible to produce basically hail of 1 inch or greater, or even the winds of like 58 miles per hour, whatever the criteria is for the local station the National Weather Service sets for a severe thunderstorm. So then you get into 50, 60 dBZs. Here's the 60 dBZ. We hit the purple. Now we're pushing up to almost 20,000 feet. That's not a lot going on right there. So, but we do justify having our tornado warnings. So to get any higher than that, pretty much you're not going to. I'll show you. I'll see if I can find my picture. I got that tornado that went through. I did a 3D scan on that. I always like to put this about 50 dBz's, 40 to 50. Just kind of give me the structure of that storm. Now, where there's tornadoes going to form in the thunderstorm cell is the southwest quadrant of that thunderstorm. So if we see rotation, see there's a little hook right there. No, you can't see that. See, I got okay, right through there. There's that little hook right there, so we definitely got rotation. And then we got the tilt of that storm. We got the updraft. I can show rotation in the upper levels. Right there, we do got a little bit of rotation in the upper levels, so we can justify the tornado warning with that. That's our base velocity, how high that goes. I only see a lot of green. Let me go to, hold on, I gotta pull this out for. That's all the ingoing colors, and then see if we can get any red in there. I don't see any. But you can probably kind of see that structure of that. I don't know if I can jump the elevations with that or not. No. Alright, let's get out of that for a second. If we go up elevations, we can see there's our reflectivity, 2.5 degrees on the radar. That's the angle the radar shoots out. So we're shooting up pretty good on this thing. Even 60 dBz's up higher than that, a 3 degree angle. So, and then we can, what you can see on these is if you look at the structure, watch this. Let me get my drag tool here. So we can see significant reflectivity right in the center of that storm. If you watch anywhere from the yellow in and then I start going up, now you can see that move over. That means you got blow off. All the upper levels are blowing off at the top of this thing. So now we got, let me get back to, hit the right button here. Okay. Significant reflectivity. And then that's pushing over that way. So in the upper levels, we're going down right now. So in the upper levels, we're pushing off with the winds that are pushing out to the north and to the east. So you can kind of get an idea of what the structure of that storm is going into the upper levels. All right, let's see if we can do a cross section here. Like I said, we got pretty good tilt, high reflectivities, and that is right inside those warnings. See if we got, it's a regular tornado warning. I'm in actually like tornado, pretty much confirmed tornado by radar or somebody on the ground. This one is a source of weather spotters, confirmed tornado crossing Interstate 80 north of Atlantic, and flying debris will be dangerous to those caught without shelter, I guess. So we got Iowa is kind of, looks like it's blowing up. Yeah, going across section. Let me get out of there. Like I said, with the dew points we've seen in Iowa, we're pretty much we get in the upper 50s. I mean, typically for really severe weather, you want to be in the 60s. Typically about 65, is where you could pretty much say your tornadoes are going to be. But being December and this low pressure system just forming up right in the middle of the U.S., this is a little bit oddball situation. Just like that low pressure that formed up pretty much in the same area and shot, it was a little bit south, I think, and then it shot up to the northeast, caused that tornado that traveled over 200 miles. If we go to the 500 millibar, we could probably see another deep trough that got cut off and just ejected this low. So it's kind of the same situation, but this one's a little bit further north, and it's going to affect these states. But I don't think we're going to get what we got. You know, we're not going to see any tornadoes that are going to cruise 200 miles like that last one did. I don't think anybody was expecting that. All right, I'm keeping an eye on the chat too. If you guys want to chat, ask any questions about this stuff, go ahead. Feel free. I'll do my best to answer them. All right, I'm going to go to maybe shoot up to, let's go up to the 850. If we look at the winds at the 850, we look for 40 to 45 knot winds at 850 millibars, and then we can judge our low-level jet. If you end up with a low-level jet, 45 knot wind jet at 850 millibars, you can pretty much say that's a significant indicator of severe weather also. Because the station plots. Now these station plots, it's only 6 p.m. on the East Coast. So another hour we'll get, this data will be updated. This is the balloon data. They launched this at 7 o'clock in the morning, 7 o'clock at night. So this will be updated. A lot of this data, you know, like I said, 7 o'clock in the morning is pretty old. So if we were to pull a sounding from this data, we would probably show pretty strong inversions toward the surface. Nothing would really indicate severe weather, just because the atmosphere was in a completely different state at that time. So right now, 50 knot winds from the southwest, 50 to 55 knot winds. Like I said, all we need is 45 to really be considered a low-level jet. If you look at these wind shifts, we got a little bit of rotation there, a little bit of shifting going on. So that shows troughing in that area right over Oklahoma. But we do have the low-level jet, though. So on the surface low, if you shoot a winds over top of that low, you can suck the mass out of that low-pressure system and cause that system to deepen. And it can deepen pretty significantly when you get up to the 40, 45 knot wind speeds. So that's why our low-pressure system just becomes so intense so fast. It is with a low-level jet. Let's go. This program puts. Which I could probably put a little bit more data on that screen too. Let me do that real quick, and then what we'll do, we'll try to do a wind shading to try to see if it picks up the low-level jet on this program. Let's go. I have to erase this first because it's just going to cover it up. Let's go upper level knots on the winds. Nothing came up, so it didn't color anything in. The winds weren't significant enough. That part of this program for the shading is designed for the jet stream. So let's go up to 300 real quick, and we'll pull. We'll show you where the jet is. And this will be pretty much your steering is your mid levels, mid to upper levels. So 700 millibar, which is about 10,000 feet. 500 millibar, 18,000 feet, and then 300 millibars, about 30,000 feet. So that'll be pretty much your steering flow. Now, if you look at this, we can add our upper level data on this and watch our winds. Let me go to. I got to put some pressure on here to show you the contours. It takes a minute to process that. See what this one does. I did if I do a balance height, this is showing rigid in the upper level, so let me get rid of that real quick. I want to do a balanced height. When you get significant weather like this, these charts, this program doesn't compensate for that very well. So I have to do a balanced height, and that will actually give me a better reading on what's going on. So, I mean, I do kind of see some ridging. If you look at the flow of this thing, let me go to, I can probably draw on the screen for you, see, give you a picture of this. So, got the winds out of the southwest curving around, but what we're kind of looking for is our contours. Actually, you can see a pretty deep area right there coming around that way. We should be pushing, this is pushing from the west. We should be pushing from the northwest, pretty much like those winds. So we got rotation there. It looks like even possibly just jet finger here. There's our trough. Looks like upper level ridging there. What you'll get with the upper level ridging, you have a low pressure system on the surface. Let me get rid of all this mess. So we have our low pressure system on the surface, and then that wind starts pushing up, and then when that low intensifies so much, those winds hit the upper levels like 30,000 feet up here, and then they'll spread out. But what that does is it's pumping that mass up and then hitting the tropopaules and then creating higher pressure in the upper levels. So that's why we're kind of seeing ridging in the upper levels. So you'll have a low. Okay, there's our balance tight right there. So it's just now completed. So now we can see looks like an upper level low there and ridging in this area. So we got our ridging right, pretty much right where our jet max is, and then like I said, the winds are pushing up, causing that ridging because you got higher pressure. So you can have a low pressure on the surface, and then as those winds push up, then you start with that ridging, and then you got high pressure on the upper levels. That's pretty much what you'll have in a hurricane. Hurricane only go up so high, and it's pumping up so much mass up to the upper levels to the tropopause. It's creating a high pressure system over top of that. Alright, so we can see our contours, troughing, ridging. And then we got some troughing going on here. It looks like maybe a closed upper level low, or this data is just being extrapolated a little bit wrong with this chart. That could happen. So you look at the if you go in there and look at the data, like minus 41, that's your temperatures, 937. So we'll go 9370 on a pressure. There's 9360. So you start analyzing each station with each contour height, then you can actually reanalyze this chart to match the real data. But 300 millibar I don't really worry about. What we're looking for in 300 millibars is a jet stream. Just try to get a good picture of the jet, and then get where our jet maxes are, the maximums. That's going to be where you have an indication of this jet max is moving into this trough, so that would deepen the trough. That's the typical rule of thumb. Sometimes that doesn't happen. It depends on a lot of other factors too. That's just one rule that you use. So if that jet max is moving into the ridge, then the ridge would build. Moving to the trough would deepen. Moving out of the ridge, then that ridge would weaken, trough would deepen. So you just got to know them different rules. Now if we go to the mid levels, like we said, with our low pressure system on the surface, then we go to, say, let's go to 500 millibar. 500 millibar is a pretty significant chart as far as data being used. At 500 millibars vorticity, look at your mid levels, your steering flow, your speeds. So let's go pull a 500 real quick. I want to do that pressure. Let's see. Do the balance pressure again. It takes a minute to process, but let's just see what happens. So I wanted to have a pretty accurate pressure contours on this thing so we can read that. And then once we get our wind speeds up to 500 millibars and the direction, then we can see what the direction that our storm should be moving to. So here, let me get I'll just put you back on the radar for now. I'm trying to process too much data at once right now. Getting froze up. Alright, starting to act up a little bit. Let's go. Okay, so I was just going to put you on back in the radar, but there ain't no sense in that. Let's go back to the charts. We just got this data came up, so we got our long wave trough to the west. Now, throw the isotherms on here. We can see if we have any kind of thermal advection. That's what we're going to look for. In the mid levels, we're going to look for our station plots, and then we're going to look for our direction. So we do see. Let me get my pen out here. Alright, let's go. With the dashed lines, those are our isotherms, lines of equal temperature. So we can see our thermal ridging in the upper level. So we got warm air pushing all the way to the upper levels. We got warm air advection. Now, since these isotherms are crossing the contours, so our contours are here, the black lines. These are isotherms. Since them are perpendicular from each other, then we got warm air advection because you're pushing warmer air from the south into the colder air to the north. So we got warm air advection in that area. That will cause a low or a trough to deepen. Now, this trough to the west, that would be the upper level support for that low pressure system that's over Nebraska. So it will always stack back toward the cold air. The low pressure, now you'll get, like, we don't have a closed low at 500 millibars, so this isn't like a super deep low. I've seen them closed all the way up to 30,000 feet. This one's just, we don't even have that. We got a trough in the upper levels, but our isotherms are parallel to the contours, so we don't really have any significant thermal advection until we get on the other side of this thermal ridge. Now we have our thermal advection over here. So as this low pressure system moves out, this trough starts moving in, then we can pick up any of that warm air advection and then cause upper level divergence. So we can cause that trough to deepen, cause significant weather. So as we push through Iowa with all that thermal advection right there, let's go back, clear this out. Right here, there's our isotherms. There's the isobars crossing, so we have all this warm air advection. Now we can have pretty significant weather in Iowa, and that'll go all the way up to, this is 18,000 feet right here. So 50 knot winds, that's a 50 knot. So we got significant winds in that area too. So we pretty much got all the ingredients we need to have severe weather through Iowa in this, as this system moves to the east. All right, another rule of thumb for that surface low movement, the frontal movement. Let's go back. We can actually put, I can overlay surface fronts on this chart. It's not going to make any sense, but it will, just because of what, just for training purposes. Watch. So we'll go. All right, here's our fronts. There's our surface low. Surface low. Cold front. Now, what's behind this front? Now, the reason I say it doesn't make any sense is because of our upper level winds are going kind of parallel with this front. On the surface, they're going to go perpendicular, push onto that front, and then that's going to be the leading edge of that cold air mass. Now, the upper levels, though, since we are parallel, we can still say, look at our wind speeds at that level, right around that, where that frontal system's located. Let me clear that. Clear that front, them fronts off there. So our low pressure system, oh, gotta get my draw tool back on here. And then the frontal system, so we got about a 60 knot wind. So at 500 millibars, we go with 50% of our 500 millibar winds. So if we're at 60 knots, 70 knots with 35, 60 knots with 30. So we can say that low pressure system should be moving about 30 30 knots to the northeast. So that's just a rule of thumb. Another one is 700 millibar. I'm not going to hit the 700 millibar. That's about 10,000 feet or so. But 700 millibar, you're about 70% of the 700 millibar winds. That's going to give you an indication of how fast that system's moving. Now, rule of thumb is like, okay, the low pressure system, we're being steered at the 500 millibar on that low. So we're in the mid to upper levels here at 18,000 feet. So we're going to see that low pressure system is going to move to the northeast. If we look at the models, we've seen that system, that's where it's moving to. So on the surface, you start coming up to these, you can't say, okay, the leading edge of that cold front, our front's not going to move to the northeast. It's going to move with the low, but the front's going to continue to push to the southeast as a high pressure system. Behind that typically will push to the southeast, and that's what's feeding this low and giving it that energy. It's pushing into that and rotating that low. So now your frontal system's a different story on how fast it is moving. You got to go back to these wind speeds in the upper levels will actually help you determine, there's one up against the front. Let me go to get that out of there. Right there. So we have some troughing right there, and then we got our cold front that we knew was pushed through, and then so we can kind of estimate that front, how fast that front's moving based on these upper level winds too. But you're also going to want to go to the 700 millibar. Then you're going to go past data. You can pull up, the last hours, couple hours data. With this program I can, it's a digital atmosphere. So I can pull that data and then plot these fronts and then see how fast they have been moving. So in real time, you can look at the radar, see how fast those storms are moving. That will give you an indication how fast the front's moving. And then where the front is located. If the weather's at and ahead of the front, you have an inactive cold front. If it's at and behind the front, you have an active cold front. So that's going to determine on the slope of the high pressure or that cold air mass. Do we have a shallow slope where the clouds and everything's being pushed up? So now if you're on the surface, you're looking up, all that weather's behind that front. There's your cold front right here. All the weather happens right here because your lifting condensation level is let me do that again. Whatever height that their partial has to be lifted to condensate, create clouds, the frontal system has to push it that high before it does become condensated, and then you get weather at and behind the front. So there would be your front. Now if you got a steep slope, here, let me just get a whiteboard up. Now on a steep slope, say big high pressure system's got a pretty steep slope, then basically what you're doing is taking that warm moist air at the head of that front and just kind of plowing it, and then whatever your lift is, you're pretty much at and ahead of the front for any significant weather, because you're just kind of plowing that warm moist air that's being pushed up from the south. Because at the cold front, your winds are going to pretty much be from the northwest, push it behind that front, and then from the southwest in front of that, ahead of that front. That's your trough, and that's where the frontal system actually lies, right there. And then coming out of the low, and then the warm front is on the warm side of the isotherms for the warm air advection. And you have the warm sector here. Now you're on the warm side of that, and then you have your winds on at the warm front now will be, so you have your low, wind circulate counterclockwise around the low, you got a warm front coming out. Winds are typically going to be from the southwest behind that warm front, and then from the east north of that warm front. So then that's your troughing here. So that low pressure system is going to be shaped kind of like that. You're going to have an area for your warm front to sit, and then an area for your cold front. And now, unless you go occluded, like I said, if the cold air catches up with that warm air, starts to undercut that, then you have an occlusion. That should be purple, and then coming into the cold front. Now, the difference on that is, these charts get a little messy real quick, but try to keep the right colors too. I mean, people will nitpick on that. But so if your occlusion comes out of your low, you got that wraparound of the warm where the cold air is undercutting the warm, and then you catch into the cold front. You're going to have an occlusion. So if the cold air is undercutting the warm air, then that's going to be a cold occlusion. So your occluded front is going to attach with the cold front. All right, now if the warm air is overriding the cold air, then let me get rid of that. You're going to have, once again, that should be purple, that occlusion attached to the warm front. And then your cold front's going to come down. So you're going to have more of a T shape. So instead of that comma, that's going to be your cold occlusion. 90% of the time you'll have a cold occlusion just because that cold air mass is just pushing in and undercutting that warm air and then creating that cold occlusion. Alright, so get rid of this. Alright, so 50% of the 500 millibar wins, 70% of the 700 millibar wins. That's going to give you the movement on your system. Let's get back to the radar real quick. See what's happening out here. So it looks like we're getting pretty intense right there. Let me go all the way to the forward one so we can pull. We got two more reports here. Tornado. Storm chaser reported tornado on the west side of Atlantic. And storm chaser reported flipped semis on I-80 and power flashes associated with a tornado. And this is in Cass, Iowa. So that's where that warning just went out of. So if we look at this system, I like to do a cross section just see what kind of tilt we have across that. I mean, we do got the tilt there. I mean, I just zoomed in way too much. I need to cut that back here. Let's see. Get a little bit better view of this thing. Alright, now twist this around. There you can see the 50 dBz shooting all the way almost to 30,000 feet. So we got the angle. We're coming down to a point. And we can pretty much say there's a tornado warning, indication of rotation on the surface at this point. I can spin that around. Okay, that's pretty much our highest reflectivities right in this area. Alright, let's go back to, we're right in that warning zone, so let me get a 3D on this thing. Go back, go the other way, trying to center that. Alright, now we get a little bit more structure. We get right into this curve. When you see that, looks like wind pushing into that area where you have the lower reflectivities. That's kind of right where you want to be. And then this thing always picks up. It never picks up like the latest screenshot, because that's all radar is. Just it's one picture, and then they just put the pictures together to make a loop. So let's go back a little bit. We'll pick up those previous shots. And then that'll give us our upper level data a little bit better. So, all right, let's get move my reflectivities around here. So, we're only up to about 50 dBzs. I don't see any 60s in there. But if I see any 60s in there, it'd be like pretty much some pretty heavy sized hail, or some pretty significant debris being thrown into the upper levels. So I'd have to I'm gonna go pull up, see if I can find that picture I got for the 3D shot. For that storm that went through Friday. But this thing is Make sure you guys can see that. And nope, you can't. Let me get to. All right, there we go. There's a 3D shot we're looking at right now. That's that warning. This I think northeast of Cass now. So that's our structure. Here's the southwest quadrant. If we had to say the tornado was there, it would be the southwest quadrant of that thunderstorm cell. And our updraft has a pretty good tilt going all the way up to about 25,000 feet. So we do have a pretty good structure on that. All right, let me get back. Let's go up to one of these cells, see if we can get a little bit better, a little bit more reading on that one. We still got the angle there. Let me go back one more time. Like I said, I got to pick up screenshots, different screenshots to get this upper level data, so I have to go back behind them storms sometimes, themselves. All right, let's go. There's a 60 dBz, 20,000 feet. So like I said, that could be some pretty good sized hail throwing out those reflectivities like that. Or it could be debris if there was a tornado in that area. I think we weren't, this shot wasn't in a tornado warning area. So another thing to look at, like I said, was base velocity. Let's go back to the base velocity. We got, there's our radar. So all the hot colors are out. Cool colors are in, so all this wind is just pushing in. You can see these, 65, 70, 80 knot winds just pushing in. This is almost like a derecho that pushes through with just straight line winds just pushing through that area. Iowa got one of those last year, that derecho, and it was just like it's like just straight line winds that push through. It's almost like the structure of that thing was just a real significant low, almost like a hurricane on land, just because of the wind speeds. And you can see the leading edge of this thing just pushing through. I mean, they're probably going to get some wind damage in this area. We got 70-mile-an-hour winds reported by law enforcement caused by a thunderstorm. They say thunderstorm gust. This was done by an automated weather system. That was a tornado. Let's see, we got automated weather system, 72 miles per hour. This 80 miles per hour was reported by an emergency manager. And zero visibility south of Adair. Just because the winds were, I guess, so strong, it was just blowing stuff everywhere. So it brought the visibility down to zero. The storm relative velocity is, you can still see that significant line right there, but that is basically the motion of the storm minus the motion of the Earth. So it's just like the motion of the storm itself. The radar makes up for the different algorithms they got for the radar pushing what direction that storm is moving. So you got the relative velocity and you got the base velocity. So vertical integrated liquid, we still got significant readings in the upper levels near Scranton and Jefferson. Let's go to the echo tops. Now we do have significant echo tops to the south. That's right in that thunderstorm or that tornado warning. And we got tops up to 36,000 feet. We got a pretty good cell down here going on too. This looks like it's got a little bit of a hook to it. There's no warning set yet. Let's go look at this thing. Maybe they just haven't caught it yet. Looks like 50 dBz up to about 20,000 feet. It does have a little bit of tilt. Looks like it's maybe, we'll have to keep an eye on that, see if it's intensifying. Let's go 3D on this thing. Yeah, it doesn't look like anything's there. Or this program's just not picking up anything for that. We just don't have the data on that one yet for the radar. Let's go echo tops. So we do have significant echo tops. We got 37,000 feet. So this one's one to keep an eye on. That might be there might be a warning popping up there. Yeah, I don't want to do that. Let's go. Trying to drag my screen, and I'm still on the volume scan. So we got a 55 knot wind, or 55 mile an hour wind, reported by a automated weather system. It was a Missouri Regional Airport, reported a gust of 58 knots, 58 miles per hour. I always say knots. From the aviation weather, I've worked in aviation weather for a while, so everything was knots. So 58 mile per hour wind gust ahead of the incoming line of storms. Alright, so when I said that one there, pretty good little hook on it. So something to watch. Let's see what the hold on, let me go back. Go back in there. Base velocity. We're not really getting the rotation from that, so that's probably why they're not throwing out a warning. Well, okay. So this one, we definitely got the rotation. We got the winds out, we got the winds in, we got gate-to-gate shear. We got some significant stuff going on. Like I said, that should be just inline winds just coming across Iowa. I mean, there could be we're probably going to see a lot of wind damage all the way through here. Got half-inch hail, estimated 65 mile per hour winds, Highway 44 and Frontier Road in Guthrie County. Alright, I'm going to play that loop. I got this thing set for a pretty long loop. I'm going to play that for a minute, and then I'm going to go search for that 3D picture of the storm that went through. I cut that all the way down to 60 dBz, and you can actually see a structure of that from the debris ball. So give me a second and I'll get back on that one. Let me go. Alright, I found it. Let's go. Let me get you guys. Let me see if I can get. Alright, there it is. This thing is launching debris. I can't move this around like that 3D model. It's just a screenshot of that 3D model. So, but this is a storm that went through Friday, and this was launching debris almost to 40,000 feet. We have high reflectivity, 60 dBz's all the way up. Let me get to the next slide. And there's another one at a different angle. Like I said, I can't spin it like I can the 3D model because it's just saved to a two-dimensional. So, but there's that angle of this thing, and launching debris right there to 30,000 feet. All the way that's when it went over Mayfield. Mayfield, I think, got hit the hardest from that storm. Not that there was any less significant damage anywhere else. I mean, this thing traveled 200 miles and just destroyed everything in its path. So here's another structure on the base velocity of that storm, and you can see that thing is just all the way up to 60,000 feet. So with the velocities, but the vortex, that's going over 30,000. So anything that got caught in that vortex just got sucked up, at least to 30,000 feet. So that was the structure of that. It's pretty cool. And there's one more. Like I said, there's the vortex, 25,000, almost 30,000. And then you're going to have significant winds always. This is a velocity chart, so I just did a 3D volume scan on that, and then but you got high velocities even up to 50,000 feet. And then there's the hook echo with the debris ball, the warnings. These are the emergency warnings. That's why there's a warning within a warning. It had a tornado warning with an emergency warning also. And then your outside larger area for the tornado warning. This is your textbook hook echo from that storm. I actually got the data downloaded for that whole most of that day, and that's why I set my radar at such a long loop, because I could pretty much play this whole thing from beginning to end on this program. There's the base velocity. You just see the rotation. There's the hook echo. So the hook echo was without the smoothing, I think, on the radar. You could turn that smoothing on and off. Plus, just show precipitation types also. That was just one of the screenshots. This is your relative velocity. You can still see that hook echo in there. Right there. Just breaking this thing down to, just the detail of what kind of significant wind shear you had through the radar. Echo tops. I think we were probably going to about 60,000 feet. Right there's a purple right there. So we were pushing 60,000 right there. That's the vertical integrated liquid. So look at let me go back to that one real quick. We got any precipitation was just sucked up to the top of this thing. Like, it was just insane. So hook echo versus the velocity. You can still see the hook. Like I said, that's a textbook picture right there for. And I did get some other 3D structures of this thing. You see 50 dBz over 30,000 feet. The green and the blue, I took the light colors and just kind of shaded them. But so you can see this thing was shooting all the way up to 50,000. There's the rotation. You can definitely see that vortex over Mayfield stretching all the way up. And that looks like almost to 40,000. It's definitely over 30,000 feet for rotation. There's a 4-screen shot. $60 dBz's, pretty much up to 30,000 feet there. Another angle of the 3D structure. There's the vortex. There's a debris ball. There's the vortex coming up. And that's without the radar smoothing. That just shows you the pixelized areas where your strongest reflectivities are. Right there in that debris ball. 60 dBz's or higher right there. So 60 to 65. I mean, that's significant. That's just insane. Look, like this was actually another thing that happened too was if you look behind this, there's your hook echo. Let's see if I can get a. Might be able to just draw on the screen. Let's see. All right, there's your hook echo right there. Now, if you look back behind that, it looks like another one forming, and then possibly even another one. But that one, I don't think it did anything. This one actually, I think there were 2 tornadoes on the ground at one time. Look at the right there in that area. Get out of here a second. 60 dBz's. We got 60 dBz in the debris field, and then 60 dBz behind that with another hook. So with the comma, I mean, that thing right there was. I think let me get to continue with these pictures. This is in Paducah, Kentucky radar until this radar went out. This radar actually I think it took a hit by this tornado, pretty close, and the radar actually did go out that night. All right, right here. So we had the vertical integrated liquid that was showing 2 cells. We had 2 tornadoes on the ground at this point. Look at that white. I mean, my logo is blocking that, but we're all the way up to, so much liquid in that atmosphere. I mean, we're pushing liquid all the way up, 60 plus thousand feet. So I mean, that thing was cranking, and we had 2 tornadoes, basically twin tornadoes. That was the proof. That vertical integrated liquid was the proof of 2 tornadoes on the ground at the same time. That was the mother storm right there by Grand Rivers that was pushing out, but that went through Mayfield. But there were definitely 2 tornadoes. I mean, I forget it was like how many warnings were set that night, and then 30 to 50 tornadoes on the ground that were reported. But this was your significant storm in your textbook scenario. This never happened, especially in December. I mean, I did put out a weather chart that, if you follow me on Twitter, Meteorology 101. It's at Meteorology, things at Meteorology_101. I did put a chart out there from a 1957 storm that had a tornado outbreak in the same area in December. And pretty much those 2 charts were pretty close. They didn't match, but they were, you had that same style low pressure system. All right, so we ran out of slides. We're going back now, but let's get back to the live radar. All right, let me maybe try to back this loop down a little bit. Let's see. Change my settings, and then I can't figure out how to change them back. So let's go. All right, I don't see it. Anyway, that's fine. Let's go back to the latest screen. All right, what are we looking at now? So we got a pretty good curve right there. High DBZ on the over north of Boxholm. Definitely going to be rotation in some of this area. That's why they're setting these warnings. I'm trying to find my radar site. Let's go right there. So those winds are out. These winds are in. So we definitely got, I mean, it looks like a straight line of winds to me, just right through that. Being that kind of, with the radar right there. Let's get on the other side of this thing. Let's go right here. Now we should see these winds kind of coming toward the radar and these going away from that radar. Downloading the latest data now. Alright, so like I said, we should see that. We're seeing that push out. Seeing some green in there. Looks like it's incoming, but that's actually nothing to worry about. Let's go. From this radar, I'm not seeing a whole lot of rotation in those cells, in those warning areas. Go up. Sometimes you'll get rotation in the upper levels. We're starting to get darker. Let me go back one right there. If that's an open area, go back down. Let's go. We're getting on the outer edge of that radar too, so that's where. Let's go with this one to the north. This is La Crosse, Wisconsin. See if that'll reach down there. And then we should see most of the winds going toward the radar. Kind of like what we had right here. But once you get that close and you have those angles of that radar shooting up, it will overshoot data. And then undershoot some upper level data. So that's why they do different angles on the rotation of that radar to try to catch the whole picture. But it does have its fallback. So this is just showing we're on the outer edge of that radar, so but all of our winds are in toward the radar. We're not catching anything in these warning areas to give us an answer. So we'll go back to this one. So we are getting pretty much 60, 70 knot winds. This is thunderstorm wind damage. Department of Highways. This is a tree on the roadway on US 6. 38 mm, 38 mile marker. So, all right, let's go. Base reflectivity. Another radar. I got another radar program, the same as this one basically, but as a composite. It takes every one of these levels and puts it all on one screen. These are just horizontal shots of the radar at each different level. So when you do a composite, I don't think I can do a composite on this. I can't do it on this one. Alright, so let me go. Open that other radar. I don't know if it'll pull up on this screen or not. We can do, let's go. I'll make it work here. Alright, this is going to be the composite reflectivity. Let me get over to that radar. Alright, this is showing thunderstorm warnings. Severe thunderstorm warnings, we got pretty much all along that line for severe weather. Then we have our tornado warnings separate. But I think on the other radar I just have I got the severe warning shut off. There's tornado. Let me go back. Download this data. Sometimes it takes a minute to get it. When we got tornado warnings, severe thunderstorm warnings, a line of weather going through like this, there's so many weather guys out there that are downloading the data from the same place. It just gets a little slow. It works those servers. So we'll do a composite reflectivity on this one. There we go. Now that pretty much puts everything on I guess I got a follower, appreciate that. Everything on every radar elevation throughout the radar, it puts on one screen. So that's why we see a lot higher DBZs, a lot wider areas. We can do the area where we can smooth this out or not smooth it. The only reason you would do that, like when you zoom in on these storms, when that's smoothed out, it looks a lot neater, but it takes away some data. Now, if I wanted to see like a hook in this storm and get a better picture of that, or any kind of gate-to-gate shear on a velocity chart, then I wouldn't want to get rid of that. Make it pixelized. Let every little pixel count. That way you can see exactly where the strongest reflectivities are through this area. Because when you smooth it, if you watch this area right there, it should just fill that in. You know, it fills a lot of that in and rounds it off. So you got to be careful with using the smooth data. Like I said, it looks pretty, but it can hurt you on a storm. And when it comes to, you know, being on the surface, if you're chasing into the storm, that little pixel, one little pixel will matter on, several miles there, a couple miles. So you know, if you're running into, you want to go into the bear's cage, then, you need to know where that is. Now, the bear's cage is with the hook echo, and then driving right into that hook echo. That's a pretty dangerous thing to do. You're pretty much driving right into the path of the tornado. If you do anything like that, you want to come up from the south. If you stay southwest of the storm, then you can kind of chase it in. But depending on how fast it's moving, what kind of roads you got, because you don't have a straight shot on the road, so you want to come in from either the southeast or the southwest and approach that storm. Just one, it depends on what you want to do to your car. If you want to go through the hail damage, or you want to video the hail, or you want to video the storm, or you want to chase that storm down, depending on how fast this thing's moving too. So let me get this thing. Only downloaded one picture. I'm not even I don't even have a loop yet. So like I said, with these things get overcrowded, and trying to download all this data overwhelms them servers. So sometimes you just don't get it. But the other program is just a base reflectivity. It's one shot. It does download all the different levels separately, so it actually works a lot better. And plus, I can do the cross sections, and I can do the 3D scans on that too. So, but this is a pretty good hook right there, man. That's looks like wind pushing into this area, so that's rotation. So when you've got these little hook echoes like this, typically you're looking for that other hook echo off of the main storm on the comma. But on these squall lines, any kind of hook like that showing indication of rotation. Let me go back to the other radars. I can do a lot more with it. Alright, so right there, a little bit of curvature right there. So it's pretty much why they're setting these warnings. Alright, nothing on the 3D shot right there. So let me go over here. Really nothing either. I just don't have the data. It's not downloading. I need to see if maybe that radar could have went down on me. This program doesn't tell me that. Sometimes if I can go on radar scope, and it will show a red radar if the radar quit. So I don't see any red on there, so it should be up. Go back and download it again. I've got a lot of stuff going on here too. Got a lot of programs open. Let me close some of this stuff out, and then we can maybe speed this computer up a little bit. I don't know if I'm lagging or not. If you see me lagging, just say something. I can just at least know. I keep trying to drag my screen with a 3D marker. So, alright. Alright, this was 500 millibars. Let's go to 700. Since we got time, we're just going to hang out for a while. Like I said, you guys got any questions, ask. I was a weather forecaster in the Marine Corps for aviation weather at Cherry Point, North Carolina. So I got experience on the desk and reading these charts and actually having to forecast the weather for different areas throughout the United States, around the world, depending on where the pilot was flying. Do got some experience in pulling out forecasts that, the weather's basically no data, just looking at, raw data on a screen and then writing a forecast straight from that. So we are 7. Let's go to 700. We're at 700. Let's get my balance, pressure, height. Like I said, it takes a minute to process, but it's more accurate. Let's go back. Let's go back to the models again. I want to see something with this is the GFS. This should go out pretty far as a forecast. Doesn't show the detail like the HRRR, but it will show us There's the line coming through, and then it goes off the screen because we only. Let's go pull up the U.S. Let's go see if we can get. Yeah, wrong one. I don't want analysis. Numerical models. Alright, long range GFS. This breaks it down to you. This site is College of DuPage. I guess that's how you pronounce that, but they break this stuff down pretty good. So now we can pull the United States and see it as a one big picture. Let's go. Alright, you can see that storm right there pushing through Nebraska up into Iowa. Let me get my mouse out of the way. And then shooting up into Canada, right through Minnesota, Wisconsin. Got a line going through Wisconsin. The wraparound looks like the heaviest stuff through northeast Minnesota. And then kind of that moisture just hanging out to the south. And it looks like that frontal system just kind of lingering there. It looks like maybe even goes stationary. Still stretching to the west. So the high pressure system. let me get my sea level pressure on here. Okay, so see the high pressure system ridging in. Just go back. There's our low. There's our front. Here's the high kind of ridging in behind that front, that cold air. Significant moisture to the north. That's all pushing up into Canada with that low. And then, like I said, that frontal system, if you look at that troughing right there. Let me get a... Alright, I'm not sure what I got going on here. Alright, something got moved. Alright, put that over top of that one. Okay, now... Alright, this troughing right there, that's where your front's going to stay. So we still got a front coming out of that low. We want to keep an eye on that and then see where, if we went forward, turn this off. Erase that and we go up. Alright, forward this. And then it looks like there's the trough. And now that would look like maybe that low pressure or that frontal system stalled out. Still troughing right there. Looks like we're ridging in on that side of the high, on that side of the front. We still got that ridge going through. And then kind of some ridging right here. Maybe ridging right there, so we're pushing into, or maybe that troughing right there out of a low to the south. So then some warm air advection because we got the wind out of the south. So warm air advection. And then up to north, we can see our thickness lines right here. You can see those dotted lines. We're pushing that thickness into that area. Thickness is proportional with thermal advection. So you got cold air advection from the north, warm air advection from the south. They're pushing toward each other, so now you got a stationary front. Now, what you have, we need to keep an eye on that low, because what can happen is we get a stationary front. Let me draw a stationary front. I mean, I don't want to take too much time, but you know, I shouldn't be changing colors yet. It's hard to see that blue in the blue. But cold front, cold, cold, and then the warm, because your warm air comes from the south, so your warm front pips are going to be to the north. There's our stationary front. Now what we have is a low pressure system over the south and a stationary front sitting there. This low pressure system can cause enough upper level divergence and form over this low. Now the low pressure system, it's already here, so we've already kind of developed, but picking up on that front, now we can start getting, that can start to deepen just because of the frontal system between the two air masses. So then you can get that low pressure system form up pretty good and then follow this front up, and it will typically follow the path of that front. It follow the path of the least resistance, so push to the northeast, and you'll have a nor'easter. So that's when you'll get significant weather in the northeast, all along the coast. And if sometimes, which we had back in 93, we had a low pressure system form for the Gulf and actually shot almost north. So even Ohio got like 20 inches of snow. So that was the I think storm of the century was what that one was. So we need to keep an eye on these low pressure systems when they're, especially when you got a stationary front. Now you don't even have to have a low pressure system on the surface for a low to form on that front. All you have to have is back at the 500 millibar level, about 18,000 feet, is have upper level divergence, or you have positive vorticity advection. So the vorticity is an indication of upper level divergence, or rotation in the upper levels. So if you got rotation in the upper levels above this front, then you got the stationary front, rotation in the upper levels, then it's Pedersen's rule. You can actually have a low pressure system form up over top of that frontal system. So that's the stuff to look out for when you got this trough, a stationary front. Anytime you have a stationary front, which we always, not always, but a lot of times we do when them high pressure systems push out from the north, they only come so far south, except for like last year, the 2020, when Texas got into that freeze. But they'll push to the south, then they'll start pushing off to the east. And when they start pushing off to the east, kind of like what this one's doing, it's ridging in, but it stalls that front out because the front is the leading edge of that cold air mass. So when that stalls out, now it becomes a stationary front. Now any significant features, an upper level trough with thermal ridging, whatever, then you can get upper level divergence, warm air advection over top of this surface front, and then create that frontal system, create that low pressure system along that front. So that's what you look for, upper level features compared to the lower level features. That's why it's important to look at the upper level charts. You can look at the surface all you want, but I've seen you have a high pressure system on the surface. Looks like, well, nothing should be there, but you have, cloudy skies being reported all over these stations, and then, you got an upper level trough that's causing it. So I've actually seen upper level lows moving over a high pressure system, creating precipitation, falling through the high, and then falling as snow. So, people ask you what's causing the precipitation, what's causing the snow. The high pressure is causing the snow because that's the cold air mass. How low is your freezing level? If your freezing level is 600 to 1,200 feet, you're going to get a mixed precipitation in that area. If your freezing level is 600 feet or less, then you're going to get snow because it doesn't have enough time to melt before it hits the ground. You need about 1,200 feet for precipitation to start to melt, to pretty much melt. So if you have, this gets pretty, if you want to hang in there on this thing, we can go pretty deep. Let's look at the models real quick. We'll get into that freezing levels and looking at a SCU-T. I might pull up a sounding too and get a little bit deeper into that on precipitation types, stuff like that. So let's go with these models real quick. We're still kind of following some storms here, so let's go radar real quick. Get to the right radar. Alright, we still got, let me get all the way out there. we have another tornado warning, east central Pocahontas County, northwestern Iowa. So this one was severe thunderstorm capable of producing a tornado was located 9 miles northeast of Humboldt or 10 miles west of Dakota City, moving northeast at 70 miles per hour. So that's a fast moving storm. Hazard is a tornado, of course, and then I'm trying to find out what was the indication on this thing. Typically going to say radar indicated, reported by someone. So we got one on the ground here. Let's see what this says. Public reported tornado on the ground. No additional information at this time. So just the public called in and said, hey, there's a tornado here. So we did get that tornado warning there. This warning's probably already gone because everything's moved out of that warning area. That has been canceled. Moved out of the warning area. Let's see, yeah. So that's that. Let's go look at this one real quick. See if we can get something out of that. I'm not getting these upper level. I'm just not downloading the data now. It kind of sucks. See if I can get a cross section on this thing. I do got the cross section. Get to. Let me jump right into that tornado where that was reported. We got some kind of red in there. Let's go. Right there. 50 dBZs at 10,000 feet. Like I said, it's only need to be severe, but they're reporting a tornado on the ground, so somewhere along the line they did get some rotation that hit the ground. It probably hit the ground and then just dissipated, but you can see the angle of that storm. So possibly could have reached the ground and created this tornado right there. Alright, so I might have to close this program out and get back in. Here's what my problem is. I'm over there. We were in that more significant storm, so I erased that anything over 50 dBZs. I'm pretty much at 60, so if we're not significant, we're not seeing it. Alright, I'm a dummy. Now, here we go. We'll go to 50. That's going to be our significant reflectivity. Okay, so southwest quadrant. Let's see the structure on that storm. Let's get back to over that tornado. There we go. Now we picked up a couple cells in there. Let's go look at the structure of this thing on a lower reflectivities. So I mean, we're shooting all the way up to 40,000 feet overshooting tops. You can see those overshooting tops in that area. Getting to the 50 dBZ mark, we're way down there. But we're still pushing up to 20,000 feet, so I don't see anything indicating anything on the ground, but let's go. Base velocity. You still see the overshooting tops just on the velocity. Alright, so right there, still not seeing anything on the surface, but we might not be catching it on that base shot for the radar. The radar might just be overshooting that. So because I think we're still pretty close to the radar. Once the storms get that close to the radar can overshoot that. So let's see where we're at here. This is pretty far to the south, so it should pick that one up. But all right, that was not what I wanted to do. Let me go. There's a small area. Alright, so probably in a severe warning here. They're not calling anything. I don't think that was in a tornado warning area, so let's go clear this up a little bit. Bring it down to the lower levels. That's our most significant rotation right there. It's really, I don't see any green in there, so I'm not really saying there's rotation. But, you know, there's our significant winds in the upper levels. So we do got some pretty good wind in the upper levels. All right. Another warning area. Try not to do that. Let's go drag this thing. Trying to recenter it. So we got another tornado, you know, couple confirmed tornadoes here. One up to the north. So I mean, this little line here is giving us some significant weather. Like I said, we hit them dew points in the upper 50s, mid to upper 50s in Iowa. So Iowa was a state that we would start seeing this thing pick up pretty good. I'm trying to see if somewhere I can view my chat on this thing. I don't know if I'm getting any chat messages or not. Alright, so let's get out of this. Let's go back. Let's say I was going to pull a sounding. Let's see, 718. There may be data out now. Actually, let me go. I'm going to have to go download it first. It's going to take a little bit. So hopefully we got, you know, 18 minutes after. Sometimes that'll give us the data. Alright. Okay, here was the 700 millibar chart with the balanced height. So this little system down here, sometimes I lose data down in let me get you over here. Sometimes I lose data down in Mexico, so it kind of, this program just closes off a high pressure system down there. We do got that ridging. We got the troughing to the west. We got a pretty deep trough to the west, supporting that low pressure system that was over Nebraska, that one that's moving through we're watching now. And then let's go with the isotherms. We'll check out our thermal advection, see if we're still got thermal ridging in the upper levels. I do believe we did at 500, so there's no reason we won't at 700. 700 millibars is about 10 to 11,000 feet. So we do got that thermal ridging there. We got, pull up some data. Like I said, this is old data. I don't think I'll try to download the latest data on this too and see if we can reanalyze. But let's go with see if I can draw here. Okay, so our thermal ridging, we still have that. Our dew points, we got, well, this is early data. We can't really go by this because our dew points and dew point depressions are so high that, or dew point depression anyway. So here's a, let me erase this. On these station plots, now real quick, we got thermal advection. That's what we need to see on this chart. We need to see wind speeds. So we get 70% of a 60 knot wind. So you're at what's that, 45 knots, 40 knots that the system be moving at. So moving to the northeast based on this flow. So you got your flow and you got your speed of what that system's going to be moving. All right, thermal advection. We got warm air advection in this area. So we are still got warm air advection over Iowa. We got all the ingredients we need for Iowa to stay pretty unstable. All right. Now I'm gonna erase this real quick, and I'm gonna put the station plots alone up there. Let's explain a little bit of this data for the upper levels. When they send out the balloons, they send back certain data. We got pressure. Well, let me get my pen back up. I'm moving the screen on you now. We got pressure, temperature, dew point, and winds. That's pretty much what we're seeing here. Now then you got these stations that are colored in. Anything that shows, we got temperature and dew point, depression. Now the dew point depression is a difference between the temperature and the dew point. So 15 is your temperature. That's pretty much where you can't see it. Let me get down here. Let's go this station right there. -7, that's your temperature, with the difference of 2. Now your dew points are always going to be lower than your temperature. So we're going to add those together. It's going to be -9. That's going to be your dew point. So you're -7, and then it's a colder -9 for your dew point. So they use dew point depressions in the upper level charts. Now the significance is anything less than a 5 or less of a dew point depression. There's a 5. Then they color that station in. There's a 4, 0. Once you get up to, here's a 14, there's no color in that station. Here's a 6, there's no color. Now only 5 or less. The significance of that is there's your moisture. You have significant moisture at that level. Let me get over here. So the way we would color this chart, significant moisture all through these areas. We're pretty clear through the central. Even though we got their storms in the central U.S., we're clear right there. But this is, like I said, that's why we can't use this data, because we know we're not clear in that area. We know that we have moisture all through this area based on that radar. Now this is a 12Z chart, so it's, this upper level data, they only let the balloons go twice a day. 12Z and 0Z. So 12Z, depending on what time zone you're in, we're 5 hours behind. That's 7 o'clock in the morning on East Coast time, and then 7 o'clock at night. So then it'll be 6 o'clock and 6 o'clock, and then 5 o'clock, 5 o'clock. So that's when the balloons are let go. And this data is only put out twice a day. So that's why we're not seeing the moisture in that central U.S., because we have old data. Being 7:24 on the East Coast right now, they've launched their balloons, but it takes some time to get that data inputted and processed, and then for us to see it and be able to download it and get it back on the charts. So I'm trying to download data. Once my soundings download, we can go look at some sounding data and pull up some of these scooties in this area and look at our CAPE. We can look at our instability and see what kind of see how stable or unstable, what kind of energy this atmosphere has, especially over Iowa. But since there's that line going through, when they launch these balloons, then they could pretty much lose a lot of data in that area too. So we could pull data to the south of that, or just a little bit to the northeast of that line, and see what kind of air mass it's moving into, and then we'll be able to determine the stability of the atmosphere. All right, this is 700, but when you put this data on here, what you're looking at, I know you guys don't have these programs probably, and you don't look at this stuff all the time, but like, if you see a surface chart or an upper air chart and you have data like this and you're not sure what's exactly going on, look at your wind directions. You got the winds southwest, northwest. I got a trough right there. That shows me significant rotation. Same thing here. Right there, they got that wind shift. So I could pretty much say my trough is coming all the way down into this area just by looking at the winds. Then you got significant moisture. Now I got moisture associated with this wind. If I put the isotherms on there, get out of this. Okay. Then we got winds out going perpendicular to the isotherms, and you can see, okay, I got thermal advection. So that's mainly what you're looking for on these charts is thermal advection, wind directions, wind shifts. You know, then your thermal ridging. You see the red lines ridging. Because if you got all this significant weather right here, you got a thermal ridge to the west. You know, that's got an indication of that pretty strong warm air advection to the in the front of that. So now getting into this area, you're going to have severe weather. That's one of the kind of the rules, that with that thermal ridge to the west, you can pull that severe weather out of there. All right, now let me get back to the surface. I'm tempted to download that data. It takes about a minute to do. Because we can go look at the radar while I do that. But let's go pull a thickness chart real quick. Pull a thickness. This is a 1,500 millibar thickness chart. So this shows what the thickness would be if you took your 500 millibar readings minus your 1,000 millibar pressure readings or height readings, and then that's what you get for the 1,000 to 500 millibar thickness. So the significance of this chart, let me get my data backed off here before I put surface data on here and clutter this thing so bad we can't see it. We'll go sea level pressure, and then we're going to go station plots, and that's going to complete this this chart. Now, the thickness chart can be used for several things. If you go to Meteorology 101 on YouTube, I think it's just Meteorology Space 101. That's my channel. There's a lot of educational videos on there for how these charts work, what we can use them for. I do some of the storm, just basically chasing the charts, chasing the models, stuff like that too. But I do have PowerPoints for presentations that show, you know, actual physics. I think we're in the book of physics now. I do a study series. About due to put another one of those out. I'm trying to get over here on Twitch, see what happens with get a little bit better audience. So I'm not familiar with how Twitch works. I just kind of got started on this thing. So if you can share these videos or whatever, get people over, help me get subscribers, and I'll stick around. If I don't, I'm going to go back to YouTube pretty much 100% and stay there. But whatever. Let's see. Now, here's what we're going to have on this chart. Let me get my surface data up, and then we can shoot over to let me get this give us a minute to process. Then I can show you just some tricks with the thickness chart, which you don't see a lot of these charts out there. The National Weather Service does put thickness charts out, upper level charts. They're a little bit hard to find, but they are there. So anyway, we got the thermal ridge. We got our wind shift from our data. We have thermal advection. So on the warm side of that thermal advection, you can almost say this is almost an occluded low. Warm front. Let me get on the warmest part of that thermal advection, you pretty much put a warm front, go back with the leading edge of that cold air with our cold front, and we look for those wind shifts. If we have any kind of wind shifts there, and then we have that cold front coming out of that low. So now we have an occlusion, an occluded low, warm front, cold front. You can place the fronts with this thickness chart, just based on these thickness lines. Like I said before, thickness is proportional with advection. So if you see a thickness lines being advected, higher thickness lines being advected, and lower thickness lines, then you have warmer advection. So there's your warm air. Back here's your cold air. And actually, if you look back here, we have a area that's closed off. And that comes around, almost closes back off. And, you know, we got a cold pocket back here. That looks like lower heights. Let me see if that is 5340, 5280. So that's lower heights right there. So that's a cold air pocket. You know, probably high pressure right there. That's the high behind this front. And then we can pick out our jet stream. If we look at our thickness packing, same thing as a thermal packing, then we can pretty much say our jet stream is pushing through here. So got a pretty tight area right there. That's where we shot up and went around. So you can actually get a jet stream that shoots up like that and comes around real tight, and it can't make that curve, and you can get a cutoff high. Sometimes with a trough too, you can get such a deep trough, it can't make that turn, so it overshoots to get a cutoff low. So I get a little carried away with the drawing. We got the thickness lines to show our jet. We can pick out our fronts. We can pick out cold pockets, warm pockets, just based on the heights. And then all these surface plots, like this red, is real low ceilings or visibility. We got snow. The weather shows up on some of these stations on the surface. So right there was snow. If we look, I don't have all of them on here, but I got like 3 lines. I got fog. We got 2 lines of mist. We got snow to the north. It all depends on that visibility with fog. Now the technical definition of fog is visibility less than 5/8 of a mile. So if you look at this thing, you can have, looks like we got, I can't remember what that symbol is right there. It's the it's almost like the infinity sign. I can't remember. It's rain showers. Let's see. I got a chart to show me. Not handy right this second, but anyway, we got this station right here. We got blue, indicates the marginal VFR. It's for aircraft. It's visual flight rules. It's VFR. So marginal is the ceiling's between 1,000 and 3,000 feet. So if we look at this thing, we could see, looks like a C11. So our ceiling is 1,100 feet. So we're between 1,000 and 3,000, so they paint it blue. Visibility is between 1 and 3 miles, or 3 to 5 miles on this. Now, what do we got there? 2. Looks like a 2 for visibility. It's hard to tell. I got a pretty small screen I'm looking at, so let's go on one of these. It's not showing the visibility on these stations. Here's one for 3 with 3 miles. If that was 2 miles, that should have been a red, because your 1 to 3 miles visibility is an IFR condition, so it's instrument flight rules, and that should go red, just like these. That's what, because visibility is 1 to 3 miles, or the ceiling is below 1,000 feet. That's the red areas. Trying to find another one. Here's snow. We got 3 miles of visibility, but we're red, so our ceiling, we got a C50 right there, so we're at 500 feet. We're below 1,000 feet, so that goes red. So first glance at one of these charts with the color charts, you got the reds and the blues. You know, you got marginal VFR, IFR, all your worst conditions, and then you can start looking at these symbols. When you got these 3 lines, you got heavy, you know, like dense fog, mist, and depending on that visibility, if it's mist or fog, these are mostly all mist. So, and then if you have the snow, you got 1.5 mile visibility with snow at that station. So when you see the red, you look for the weather. What's the weather? Is it fog? Is it mist? Is it snow? Is it rain? What's reducing that visibility? So, and then if it's not reducing the visibility, then you look for the ceilings. Then what are my ceilings? So if I go blue, red, then I want to start looking at them ceilings. Like 600 feet, 800 feet. I want to see what's happening with those ceilings, so I can see my most significant weather is in these areas. Now, like I said, now this data on the surface, this is more updated than those upper air charts. The upper air charts, we can only get that data every 12 hours. The surface data, we can get pretty much every hour. There's observations put out by stations across the United States every hour, 24 hours a day. So I downloaded this one. It's been we've been running here just over 2 hours, so a couple hours ago. These are good for about 21Z. That was about 4 o'clock. That's about the time I downloaded that. So it was updated at that point. It's 2 hours old now. So we can go update the latest data, reanalyze this chart. We should have the updated data for the other, for the upper air data too, since it's 0Z. I'm still downloading for right there for my sounding. That takes a while because so much data I'm downloading. Upper air data across the United States, so it takes a little bit of time to download, especially when I'm streaming. I'm using all my resources on this, so I'm hoping I'm not lagging and just hanging out there, So let's see if I can see myself on the. I don't know if I'm freezing or not. I can't tell, but I got one viewer. That might be me. All right. We are going to download this data, and then we'll go back to the storm, see what's going on over there. Alright, I don't need this over here right now. We can get rid of that. Give us a full screen. Alright, let me see. Still in Iowa, we got tornado warning after tornado warning, so we actually got a lot of reports come up out of this too, so got a pretty good line. Let me go all the way up. Let's see, here's our latest. Here's what's on there now. We got tornado confirmed, approximately 6 miles south, Algona, and that is reported by an emergency manager, and then public reported tornado on the ground, and no additional information at this time. That's one. I think we already read that one. And then we got 1-inch hail reported by an emergency manager. Quarter size hail reported at Highway 3 and Interstate 35. So we got some significant hail coming down in this area. It's right back behind that. That's where that cell went through. Looks like there was a tornado warning there, and that is radar indicated rotation. So nobody spotted it. It's just showing rotation. So if you see these areas of blank that are coming in, looks like we do have some rotation in that area. We got 60 dBZs right there. So let's go to see if we can cross section past that. I have to go back. I don't know if I can catch it or not. That's the problem with this thing. Find out where that was. Okay, let's go back to right there. All right, there it is. That's the screen we're catching, basically the back couple screens on that loop. All right, so got pretty good storm till high reflectivity is at 20,000 feet at 60 dBz, so we're cranking pretty good on that, and definitely could be that's a hail producer with the with that cell holding that ice in the upper levels to cause that reflectivity. So you got something bright going on up there. It's either debris from a tornado, and it's not likely 10 to 20,000 feet, on this small of a cell. Not that it's not possible, but most likely you got some pretty significant hail. And then you look at this tilt of the storm. If this thing was just vertical straight up, I wouldn't be too concerned about being a tornado maker. But since you get tilt, now you can get that rotation, and that's showing your updrafts coming up, and then your downdrafts start coming down, and then you start getting wrapped around and create that vortex. So that's why you're looking for that tilt inside the storm. Just like a low pressure system on the surface. When you look at a low pressure system and analyzing that from the surface up, you want to see stack on that system. You want to see that low pressure system or that upper level trough. You want to see that stack back to the cold air. That's where you're going to get a significant, you got a significant system. Like this one, I'm not there yet. I'm still downloading data. But where that system was in the central US, when we go up to the upper levels, we get a closed low. If you have a closed low or a trough, but you want to see that low stack back to the cold air. Then the troughing stacking back. That's why we've seen the low pressure system was over the central U.S. and then it was stacking back. And by the time we got to that trough, it was pretty much over the western U.S., over the Rockies. So that did stack back pretty good for that system. And we do have a pretty significant low pressure system on that surface too. So you see how strong those winds were, and then that was like a 992 or 993 millibar low. Like I said, it wasn't the deepest low we've seen, but it's pretty significant and pretty wound up for the winds that were around that thing. So the upper level support was there for that. If you start getting upper level ridging, I mean, you can get the upper level ridging, but you don't, you start getting, you want to see closed lows above that, or baroclinic troughing. You want to see major short waves. Now, baroclinic was just the trough, and then the isotherms crossing the contours. That's baroclinic. They're off from each other, and you'll get the indication of cold and warm air advection. That's what is going to get you the upper level support you need for a system like this. So if this thing goes severe on the surface, anything that's thrown up in the upper levels, you're still unstable in the upper levels. So it's going to continue to go up. You got a level of free convection that just allows it to keep on going. Now, if you had a barotropic system where the isotherms are parallel with the contours and you got a more stable environment in the upper levels, you throw that air partial up, it wants to come back down because that stable air is pushing it back down. So that's going to suppress these storms. So now you're not going to get, that significant severe weather that you would have on a system that's baroclinic or unstable in the upper levels. All right, so like I said, you got any questions, ask. Go to my YouTube channel. There's a lot of information on there. I got my website, meteorology101.com. There's a lot of information there. Reading through it, trying to understand it, decipher it, it's probably pretty hard. I don't have anything set up on my website for comments or anything like that. YouTube, you can comment all you want. In these rooms, you can comment. Like I said, I'm new at Twitch. I'm getting used to this thing, but it's going to take me a little while to learn all the ins and outs. Plus the programming I'm using, OBS, and everybody else uses Streamlab. I had a big major issue with lagging on Streamlab, so I couldn't use it on mine. I don't have that powerful of a computer. So I got a tablet, and it's basically a desktop style tablet with the keyboard and everything. But I can grab this thing, throw it in the car. I got mounts in the car, and I can go chase if I want to and have all my data here. So that's why I use the tablet instead of a desktop. Alright, let's go. Approximately 6 miles south. Alright, turn my volume off here, and then I can maybe go if anybody has any chatting. I don't know. Alright, so I'm a little behind, but if I think I can see the chat now if anybody has any questions. All right. Tornado warning. That is radar indicated rotation. Let me get out of that and get back up there. Let's see what if I can go to. We have three. Currently, we have 3 tornado warnings. I'm showing. I'm gonna blank out my screen in a minute. I'm running low. I'm running slow just because I'm downloading so much data. I got that weather chart data downloading, the Scooty soundings downloading, and I got this radar downloading. So, like I said, I'm uploading for a stream. My resources are pretty much spent. Alright, then it will go blank. Now we gotta, hopefully it reloads that data. Basically, I just clicked on a warning to get to it. Now we got the 3 warnings. That's all we're having. We're just a little slow updating right now. We got 3 warnings out there as far as tornado warnings. It looks like 11 severe warnings throughout Kansas, Missouri, and Iowa. Okay, so let's go break down this cell a little bit, see what we got. If I can back up a minute here and then do a cross section. That's pretty much it. This is radar indicated rotation on these storms. A little bit of tilt. We're pretty vertical. We're not real significant there. It's probably just a rotation indicated by radar. Let me get my screen back up. I want to see my base velocity. Yeah, I don't see any rotation there. Let's go in the upper levels. It just disappears right away. I mean, there's really nothing there. I don't see anything. So let me go turn on my warning areas here. I can get, here's precipitation type. Let me go, that's precipitation type. It turns to green. Turns all the blue green. Any of that blue can be a precipitation type, or it can be ground clutter. So most likely a lot of this is rain, though. Some of that lighter blue out there could be ground clutter, or just a lot of moisture on the ground. And plus, like, well, I mean, by ground clutter could be trees, stuff like that the radar just kind of reflects off of, picks it up. You'll see a lot of that around radars. Pretty consistent. They do a pretty good job of filtering that out, though. So, all right, let me get a little curvature right there. Got a little bit of a tilt. Nothing, it's nothing heavy though. Like, we're not shooting way up to, let me go back. We're going up to about over 20,000 feet, 50 dBzs. There we go. Almost hitting 20,000 feet. 49 dBzs at 20,000 feet. So I think we're, pretty significant right there. Just one isolated cell, one little area. But so definitely could be some rotation indicated by radar in that area. I'm not seeing on the velocity. Same thing with that one down there. Not what I wanted to do. Let's go. But there was 2 confirmed tornadoes, it looks like, down here. Tornado confirmed approximately 6 miles south of Algona, and that one is reported tornado on the ground. No additional information at this time. So we did have, let me go back here. We're kind of far from the radar at this point too, so it's hard to, we could be overshooting some of that low level winds that for this radar is just not picking up. All right, so our tornado showed. They're always usually late on the tornadoes, but just with time it takes to, you know, get reported and get put out there and then uploaded to this program. So we got some darker winds right through there, but not really like, you know, the red we need to see for that rotation. All right, let me go back. Go right here. 3D. Alright, what do we have here now? Drag this down. Overshooting tops almost up to 40,000 feet. We're getting into the 50 dBz's right around 15,000, almost 20,000. Right above that reflectivity, but we're not no major structures there, man. We got a lot of this stuff it looks like it's elevated. So let me make sure I'm on the surface too. I'm on the bottom degree of the radar, so let's get out to our latest data. Pretty good line going through. You know, isolated little tornadoes, probably touching the ground, coming back up, causing some damage, some wind damage, stuff like that. Nothing like we had the other night though, last Friday. That was historical. That's I don't know if we'll repeat that for a while. All right, I'm gonna go see if my data is downloaded yet. All right, so I need to find out if my upper air data is updated for these charts so we can see the new update upper air charts. Alright, I'm looking at the surface chart and trying to pull some sea level pressure, see how this thing turns out just based on this data. Getting a little high pressure and some low pressure fighting against each other. I think this data is getting a little skewed on the over the Great Lakes region, so I'm trying to even it out. We get a change some settings. Basically, what happens sometimes on this program, we get high pressure and low pressure pushed together. We get that strong pressure gradient, the high winds like that, and then this system gets they kind of get tied together. The computer kind of gets confused on the data, but I got it straightened out now. So let me go to the surface chart. Now our low pressure system has moved up over to Minnesota. We still got that deep trough all the way down into Texas. And put some isotherms on here. We know we got thermal advection through these areas. To the west of that low and to the east of that low. And we got a significant, pressure gradient. So there's our thermal ridge on the surface. Tight thermal gradient strong thermal advection behind that low. So that's what's that troughing, that where you're going to get the weather is at and ahead of that trough. So here's the let me get to station data. I don't want to overcrowd it. Make sure I'm set right now. Let's see what we got for. Alright, we still got some low ceilings around the center of that low. Marginal VFR, IFR, snow, looks like rain there. Mist. Definitely going to have thunderstorms, all that stuff. So these, sometimes, it's not reported on these charts. Sometimes you'll see a thunderstorm in there. It depends on what data I catch and if it's actually been plotted. So what we got is... Get my tool out here. Alright. There's our trough. Cold front. You can see this wind shift. See that out of the northwest? That's more easterly. So we know our cold front goes through there. So now we got a shift right here. So that front's going to go back right through there. So now with that front coming out of that trough, going back, now we do have troughing. Try to see this line again, right through here, right through there. Now we'd have almost like a prefrontal trough. So we got a prefrontal trough moving through, and then the front moving through. That's the cold front back here. Now if we look at the data, we're going to go 69, 69, 52. So we know our front's right there, separating those two stations. 43, 38. So there's our cold air. All of our cold air advection. There's your cold air mass. That's the front, is the separation between air masses. Leading edge of the cold air mass is the cold front. Then the warm air, pretty much the same thing. Like so this one though, with this thermal ridge, we're not just going to throw a warm front out here either. So we got to find out exactly where that warm front is. We did download the latest data. We could just throw our let the computer throw that up there. Right. See, the computer's getting confused on the prefrontal trough, a front, and now sometimes what it will extrapolate is like, is it, get my draw up here, if it, like cool air right through here on that front, and cold air back here. You know, sometimes it jumps some temperatures and it starts seeing that, and then these, you know, the computer that analyzes these fronts kind of throws two fronts on there. So separating, thinks there's like 3 different air masses. Now that's why you have to pretty much get in here and analyze this data yourself. Come on, erase. Alright, I'm erased. Southerly flow. What do we got? Looks like 64, 67. So 50, 43. And we do have a warm front pretty much right there, right in that area. So we'll pretty much stay on the warm front, the warmest part of that thermal advection. And then we're stretching all the way down. Now another thing, look at, I'm going to go pull, I'm actually going to go erase this. I'm just going to put that on here alone. We can analyze this kind of ourselves. just lagging behind a little bit here, so give it just a second. Okay, so I got about 85% of the data on this chart out of the 100%. If I put 100%, there'd be so many stations plotted you wouldn't even be able to see this data. So that's why we only get a couple plots per state. So you can imagine the data that's missing, just based off of that. How many stations are in one state, and we're just using 2. But let's see. Yeah, let me get my pin back up here. Trying to drag the screen. Alright, wind shift. Let's look for this warm front. I'm going to see if I have any significant shifts on that. There's a little bit right there. But with the thermal ridging, I don't think I'll have a whole lot. I got 61. There's a 75. 67. So if we had to put a warm front, almost have to be right through there to start with. 65, 67, 76. That's not it. That's 176. That's pressure. Let me clear that out. 66, 67, 61, 64. 63, even further to the north. 50. I mean, I'm getting a little bit there for a temperature difference. Warmer air to the south. So our warm front's just kind of, there's our warm sector. And then we jump back from 74 to 69. 53, 69 to 53, 52. So, and then we do have our wind shift right there. So our cold front's pretty easy to find. Now another thing to look for, say your dew point's 58, 60, 56, 53. I mean, we're not real hateful, for a big difference there on that warm front. On this cold front, we're going to look for 29, 34, 63. Now we got a heck of a jump. So 57, 27. So there's our front. Now another thing with the dew points though too, and being December, you don't look at it a whole lot, but in the springtime, Tornado Alley, you're gonna want to see where your dew points down in Texas are. You got a 57 and a 27, 63 and a 27. There's a 26. You would pretty much have a 62 and 28, so you could have your dry line right there, and that's basically the difference between these two air masses. And then you get that instability, southerly flow pushing all that moisture over Texas. Here comes a dry line. There's your lift, and then you can get explosive cyclogenesis just from a dry line, a capping. Over the surface, you get temperatures increase with height. That could cap that surface, hold up moisture to the surface, keep pumping it in, and then you get a dry line come in, and then you get the inversion breaks where the temperature increases with height. Well, if you heat that surface to this upper level temperature or cool that upper level temperature to the surface, now you break the inversion. There's nothing to cap that, holding that moisture down. Now you got your lift. And then you got, boom, your explosive cyclogenesis that shoots up. And you hit your level of free convection, and pretty much severe thunderstorms right all over. It can happen in Texas, Oklahoma, during Tornado Alley. That's where you get them thunderstorms just pop up. Boom, next thing you know, you got a tornado on the ground. Alright. So, let me see where we're at here. Still not downloaded on my data for my sounding yet. I want to try to get into the soundings just a little bit. We've been going for what, about 2.5 hours. I don't think Twitch might keep these on here for a couple of days. I don't know if you guys can get to them or not. I'm not sure how all that works. I do record these videos too, and I may upload this to YouTube. Might have to cut it into 2 parts. I mean, it's a pretty long video. Anyway, there's our low pressure system. We're pushing through. We got significant ceilings dropping down and precipitation. Let's go back to our radar. I'm going to see. I probably got some charts. I probably got some other charts. I want to go to. I download a couple of charts, different charts too. I have an automatic downloader that goes to the internet, downloads GIF files from one weather page, one weather website that does forecast models, and I can download those as GIF files, and just the picture itself, not an animated GIF or anything. But go look at those, and it's just basically the same thing: a thickness chart, GFS, and just your typical model run. Just different. Everybody's data on the GFS is pretty much the same, except for they start changing the colors, and depends on how their graphics look. So if I go like, get out of that and go to the models. Let's go look at this thing on satellite real quick. Actually, kind of jumping around here. Let's go. We forwarded through this. No, we called that a stationary front. And then we had to watch out for that low pressure system that was down in the south, but we can watch for any low pressure system to start forming. We see that high pressure ridging in. Looks like its front goes stationary. Then we get a little bit more convection that pops up and then kind of dies out, and then pushes through the Ohio Valley, and then over the mountains gets a little convection, a little bit over right off the coast of Texas, and then it looks like a 1030 millibar high. Alright, now that one's one we could watch out. There looks like a nor'easter. And then it just shoots up the coast. So we'll see if that develops in a few days. Let's see where that comes from. Let's look across Texas. This is Monday, 10 o'clock in the morning Eastern Time. December 21st. Shoots across the Gulf and then up the East Coast. That's pretty significant deep low right there. So we can get right there, South Carolina, we can get some pretty significant weather. Actually, even over Florida, right there, crossing in through the panhandle of Florida, and then into South Carolina, off the coast of North Carolina, out to sea. But then up to the north, it just looks like some unstable wave or some little clipper system pushing through. Just looks like an Alberta clipper maybe that pushes through there. High pressure finally drops to the south, clears the east coast out, and then we get some another system. Looks like a Colorado low, jumps out from the lee side of the mountains, and then starts causing convection over. Looks like Missouri, Illinois, Indiana. We could get some significant weather in southwest Ohio. That's where I'm at. So, all right. These start getting out, past 5 to 6 days or 10 days. Where these things get pretty inaccurate. But there's another system, and that gets off the East Coast and becomes a pretty significant low. I mean, I've watched for them one of those, like that system that popped through. The models did pick that up at 500 millibars, pretty good, but these storms right here that are going to pop up and become like the nor'easters right there going up the coast. All right, we got a download here, so let me go. All right, let's go back here. Okay. See where these low pressure systems pop up. You get one pop up over the Gulf or over Texas, and then that can wrap around that high and just steer straight to the north. and cause us some significant weather. So, all right, that's pretty much that. Let me get back to the beginning. I'm going to pull a sounding. See where I'm at here. All right, let me go pull a sounding for Iowa. This is still 12Z data, so we didn't really accomplish anything there. Let's go back. Over Minnesota, let's pull that sounding. Still 12Z data. So you can see the reason, one thing it tells you is 12Z data too is like this, these inversions right here. Yeah, let me get over here too. Probably going to change the way the screen looks. There you go. So inversion. That's when we talk about capping, the warming with height. On these QTs, you can get capping, you get warm moisture being pumped in under these inversions, and then all of a sudden, this surface temperature either warms or that upper air cools, and that breaks this inversion. And then that's when you can get all that moisture that just pumped in there and created an unstable environment being capped off and then just explodes. So this data really does us no good. Go through this real quick though, like if we're definitely above freezing, here's our 0 degree line. We're above freezing, we're warm. Here's our freezing level. So any precipitation, so right here we got the temperature and dew point right that close to each other. Remember on the charts we only need 5 degrees to have significant moisture. So anything is kind of the same principle here. If we have anything less than a 5 degree difference between the temperature and dew point, then we could say we got clouds there. So we got significant clouds right through this area. We have a big dry area. And don't worry about the capping on the surface. This is going to be basically what you would have. You have the moisture availability and the low level winds. No winds really. But we got, look, 20 knot winds. Way too windy. 20, 30 knot winds right here that are going to be blowing this all over the place. That will give us our instability in our cap. But if you had a light wind, a little bit of moisture, capping like that, then you'd have fog over that in that area. You could have some advection fog or radiation fog that just gets capped off and just sits on the surface. All right, so significant moisture in the upper levels. Dry area. If this ended up raining, what could happen is it could fall through this dry area, evaporate, and then never hit the ground. That's one possibility. Another possibility, it could rain, evaporate. Evaporation causes cooling. So then now you take this temperature and you'll be cooling this temperature. You cool it down enough to become saturated or get close to saturation. One thing you're going to do is you're going to drop your cloud bases lower because your rain's evaporating as soon as it hits that dry pocket. Cools this down, brings your temperature and dew point closer together. Now your cloud heights are dropped. This is a pretty significant gap. You're probably not going to cool this down to that level and bring your dew points up to be able to completely get the rain at the surface. Now you probably, depending on how big them drops are, if they evaporate fully before they hit the ground. Now this will be like cooling this as they evaporate, depending on how big the drops are, how heavy. Then this is pretty wet, so we'd have to see what kind of moisture levels we have. We don't have anything for energy or anything else. I mean, this is in the morning, so it really doesn't matter. Your CCL is 3,000 feet. So your just from daytime heating rises an air parcel, you're gonna form at 3,000 feet. Let's go look at this real quick. Let's call this our cloud basis. We get rain. That falls through, what is this, 850 millibars. That's about 5,000 feet right there. We got 700 millibars. That's about 10,000 feet. So what, about 12,000 feet? So 7,000 foot gap. You're probably going to be evaporated before you hit the ground on that moisture. So you probably didn't see rain showers, even though we have some pretty thick clouds in the upper levels in Minnesota this morning. You probably didn't see a lot of rain showers, but with that upper level moisture, you're setting up for, later on having that moisture availability to create instability and bring you back to, these thunderstorms. All right, so like I said, we don't. This data is still 12Z. It's old. But I'd like to see what we have for the new data if we want to, because we may have something here for instability. Let's go. I could analyze these charts too. Let's go. Move this out of the way. Pull our cape. There's going to be no cape. So our cape is our instability. How much energy, potential energy, the atmosphere has to go severe. That's your potential energy, your cape. So, really nothing going on there. Let's go. Contrails. Anything you see up in the air for contrails flying out of the back of planes is going to be 25,000 feet or higher. That's like it's not even 25,000. This is 30,000 feet, so 30 to 40,000 feet. About 250 millibars is 34,000 feet. So about 34,000 feet is what a plane would have to fly to leave contrails behind it. They typically will fly about 30,000. Here's your inversions, all of your inversions that cap the atmosphere. Anything that's considered a temperature is increasing with height. You have a subsidence inversion, or radiation inversion. As I say, you got radiation fog on the surface. If you have moisture, but you have too much winds. These winds on the surface, if you hit anything over, say, 6 miles per hour, it could dissipate that fog just because you have too much mixing. So the fog layer, here's your fog layer. There's that right there on the surface, wet fog, 300 feet. So let's go. But 300 feet, that's still, 300 feet of cloud layer, causing fog on the surface. So you could still have it. But I wouldn't count on that too much, like I said, with them winds. You have to have way too much. The winds are way too strong. Here's our freezing line. I don't have anything telling me the height on this. Actually, right here we have freezing level 10,483 feet. So right there is 10,000 feet right there, about that 700 millibar. What is that? 9,800 feet. So 10,000 feet is your freezing level. Now, if we went with severe storms, too stable for upper level thunderstorms, have a little bit of a strong possibility, mostly a weak possibility for thunderstorms, and then we got no potential at all for hail. I hope you can see that on the screen. It's kind of cut off, but here's our storm character: multi-cell, supercells, ordinary cells. If we get, right down here, we got the dot where we pretty much have no significant, no chance for them storms at this time. This is 7 o'clock in the morning. These charts are old. Like I said, this changes throughout the day, so that's why I wanted to try to update the latest data. It didn't catch it. Like I said, when they launch those balloons and process that data, it takes a little while to get that data into the system to where we can download it and then analyze it. So if we're still on here, it took a long time to download that data anyway because I got so much resources on my computer being used. But I I can try it again, but I don't think it's going to be worth the wait. We'll have to cover that on another video. So, but with this program, I do have another part of this thing. I have to forecast the max temperature. I'll call it 50 degrees up there, and then probably not that high. Let's go like 40, 43 or something, and then if I calculate that, now I can see clouds. This SCOOT will show me I'm going to have high clouds, mid clouds, and then some stratus toward the surface. So this will, based on this SCOOT, you can put your forecast temperature in there, and it will show you, different types of different cloud layers, stuff like that. We got also, let's look at there's our CCL. That's our convective condensation level. That's what an air partial has to be lifted to, just by heating, surface heating, to saturate and have the potential to become convective. So that's basically your low level clouds would form at that layer. But the problem is this CCL is so high, that's no longer a low level cloud. The stratus layer, we got stratus down here, so here's a CCL at the surface. Now we got, I don't have anything showing me that height. Looking at about 900 millibars. I'm at 925 is 2,500 feet. So about 2,000 feet is where you'd have a cloud base on the surface, close to the surface, for your low level clouds. And then I'll close this out, and then I can have readings as I put on this chart. They'll show me, I got readings to the left. You can't see them. I can't move them either. So now this will give me the height of that inversion. It'll be, let me find it on this, 2,400 feet is the height of that inversion. So pretty much if clouds formed in that area, your base is going to be about 2,400 feet, but then anything below that is going to be capped by that inversion and be mainly fog, just on that, just based on this radiation inversion. Now we did look at that, and that was like 300 feet for the fog height, having 300 feet surfaces. Our freezing level is 10,000 feet, so you never get snow out of this. The tropopause level is at 40,000 feet, so if you have to hit 40,000 feet with these storms to have overshooting tops. No prediction of hail, nothing severe whatsoever. So I'm just going to close this out because this isn't really helping us. Let's go. Try to show you some other features on this, but like, there's a lot of tricks to this. I have to get in the book to look some of this stuff up, because it's like if an air partial travels dry adiabatically and it crosses the dew point, then there's just certain things that can happen based on those forecasts. So that's where they get the CCL, the LCL, your lifting condensation level. So if I pull a lifting condensation level, this is the LCL on this is, since you have that strong inversion on the surface, it's only 127 feet. So that's the height that an air partial would have to rise to create a cloud layer, and that's be forced up by something. It has to be in a lifting condensation level. It's lifted by a front, lifted by mountain range, low level convergence. Something's got to mechanically lift that air partial, and once it's lifted up to 127 feet, you'll have clouds form. So with this radiation inversion, any amount of wind whatsoever, could create some low level convergence, lift that up, and you'll have fog at 127 feet. Now, like I said, with these winds over here, it looks like 10 to 20 knots. I would say there was very little fog in that area. We could pull some weather observations at this station and find out for sure. So KMPX, let's go, let me go do that real quick. Let me get you back to the radar real quick. I'm going to see that. Alright, let's go look at this radar. Just Alright, keep an eye on that radar. We'll go. I'm gonna pull up these VTARs for that station, and we'll go back to this morning. What did I say? KMPX. Nothing. Let me go back. Where am I at? KMPX. I don't have any station reports for that area. KMPX. No METARs. Alright, let me find something close to that. Still got tornado warning after tornado warning, just following on through with those cells. So that's a pretty significant system going through. Let's go. Let me find. Okay, MPX. Let's go. Well, I have to start over. Okay, we have an inversion. We have a pretty good inversion in Illinois. See if there's any fog there. We got 20 knot winds on close to the surface, so we shouldn't have winds there either. KDVN. Let me go to that one. I know you guys can't see what I'm doing. I'll pull it up in just a second. I'm just pulling METARs. It's a meteorological observation that's reported every hour. Alright, so we had some significant winds here. Alright, so if we look at the... Let me get you on the same page now. Alright, we look at this METAR data. This is all the observations that were sent out every hour. Unless there's a special observation based on the start of a thunderstorm, end of a thunderstorm. Cloud layers drop below 2,000 feet, 3,000 feet. You gotta have specials sent out at them times. So if we look at this data, like I said, we were looking for fog. So we were looking at in the morning. That was at 7 o'clock in the morning. 12Z. Here's 11:21. Here's about 12Z right there. The 12Z report. Gusting to 25 knots, 10 miles visibility, broken 1,200 feet, broken 2,700 feet, and overcast 3,100 feet. 3 layers of clouds right there on top of each other, and then unrestricted visibility. Gusts of 25 knots. No chance of fog whatsoever. Now, these ceilings went from 900 feet to scattered at 900, scattered at 1,200 overcast. But we still had a ceiling the whole time. It was broken. If it's broken to overcast, it's considered a ceiling. We had overcast at 900 feet, so we did have a low ceiling. And we had ceiling 800 varying to 1,300. If you look at that, the ceiling was 800 feet varying to 1,300. So it was just an uneven ceiling and all over the place, 8 to 1,300 feet. So you had a real low ceiling in the morning, but the winds on the surface were way too strong. Well, we'd have 14 knots sustained, 22 knot gusts, 13 knots. Never going to get fog. Never going to drop the visibility. Going to drop your ceiling. We had that inversion present, but so we could drop that ceiling. There's only so high the moisture could go. When it hits that inversion, it stops. Give warm moist advection into that area, and it still just caps it. So you'll get a low ceiling, but with the surface winds, you have way too much mixing to become fog or restrict the visibility that much. So we didn't even drop below the 10 miles. 10 miles is a automatic unrestricted. 7 miles is unrestricted visibility. 10 miles is like the default for these automated systems. This is the automated that shoots out beams, shoots out a infrared beam to detect how far out the visibility could be, how far up the sky the ceilings could be, and then obviously measures wind speed, direction, temperatures, dew points, pressure, and then any significant data like a peak wind, min and max temperatures, sea level pressure. So you get a lot of data off these, and you can tell what's happened with the sky as that system went through if you pull all the METARs for that station. So we pulled the closest METAR to where the tornado hit in Kentucky. We pulled those observations and see what observations were put out. I mean, it depends on if there was a weather station in that path. Obviously, they would take cover. They wouldn't go out and do an observation and say, tornado on the ground. They'll report that out there, but they won't. They're not going to sit there and type all this information and send it out as a observation. So, all right, let's go. Back to the radar. Maybe do some. I think I had a few screens back. I had a pretty good curve on it too. So let's go. A pretty good curve. Right there's one. Let's go see what we got on that. Try a cross section. And I don't really see nothing there. Get this out of the way. Obviously got enough to be severe. Let's see what that warning says. Storm, which prompted the warning, has moved out of the area and it's been canceled, obviously. Let's see. Severe thunderstorm warning remains in effect for northern Freeborn County until 7:30 p.m. So it's probably another indicated by radar. Rotation indicated by radar is most likely what set this warning. Alright, let's go all the way to the end. Yeah, trying to do a cross section, don't want to do that. Let's get Alright, let's see here. Got a pretty significant cell there. Let's see what our warnings are. We're getting warnings. One in Howard, Iowa. Right there's our only other warning left for a tornado. Still got plenty of severe weather. Severe thunderstorms. Let's go throughout Iowa, Missouri, and Minnesota. So we got pretty significant, severe thunderstorm warnings out there. Go zoom out on that. There's what we got. That's all the warnings. Obviously out of the radar area. 70 knot winds, 60 knot winds, all reported. Train spotter reporting numerous trees down and wind gusts 65 to 70 miles per hour. Alright, so we got one more tornado warning out right now. Probably rotation indicated by radar. I would probably guess on that. Let's go. I don't know, precipitation type. Let's get this. See, I just being pixelized like that, it makes it pretty rough. But if you want to start analyzing these to the just detailed, then you're really this detail is going to help on that pixelization. So the smoothness just kind of makes it look neat. Now, believe it or not, like this radar system, the WSR-88D, came out in 1988, and it's been the same radar it's used since. Just different programs to extrapolate that data. Now, when we first started using the WSR-88D, we had two big, giant, humongous monitors right next to each other. This touchpad keyboard that was like probably 3 feet by 3 feet, sat right in front of this thing, and you just touched the thing, and then you got it was like a 10-step process to do a cross section. You couldn't just click on a screen like this. There was no mouse or no regular keyboard. no shortcuts. It was just you had to type in what location you wanted, um, the second location you wanted, and do a cross section from one point to the other, and then you would get your cross section. But every screen that came up looked just like this. So as you're trying to extrapolate that data visually and trying to determine where that storm is going to pass, where the strongest part of that storm or possible tornado was going to pass, that was, this was the data you had to look at. There was never any, there was not any till way later where we could smooth this thing out and just made it look like this. I mean, pulling a cross section, I'm just clicking on one little button and then dragging my mouse across, and boom, we got a cross section. I mean, that's, when I was in the military back in 0203 is when they actually came out with the latest. It was actually put on a PC on a Linux-based system, and all that data was put into there, and we were like, look at the resolution. And to do those cross sections, it was a heck of a lot easier because there was a mouse. It wasn't just a click and drag. It was click 2 points and then do a couple other steps. Nothing like this, but that thing was it was a heck of an improvement compared to what we had. Plus, but you could never do the 3D. The 3D model, these 3D, they never came out till later. Like, I'm not sure when they started this, but that makes it pretty nice as far as seeing your structure of your storm, how far it's going up, how intense is this thing. I mean, because you get tornado warnings kind of like this all the time. Like this one right here is radar indicated rotation. So if you got any gate to gate shear, let me go turn that smoothing off. Turn my radar off. Hold on a second. Okay, change the velocities. Now we got some now we can see that rotation, and now that's why we got. That is why we have the tornado warning. So cool colors. Cool is in. Everybody likes to be cool. So cool is in toward the radar, and hot colors are out of the radar. So winds crossing this radar right there is basically from the southeast. That's what's pushing through at that radar. Now you get these storms pushing through, and you get rotation areas like this. That's why you're getting the tornado warnings. Now that button I'm pushing right there is like for a different style velocity. It's like picking up little minute stuff. So, the radar is still going to indicate rotation at those areas. But when I turn that off, now I don't see the rotation. But that just tells me it's not a significant rotation. I mean, we still have the tornado warning. They're going to put the warning out. It's legitimate because of the rotation, but is it likely that a tornado is going to land there? It's a lot less likely than any area over here. So we got, that's tornado warning because it's purple. This red is a let's see, what is that one? Tornado warning. Let me see what the difference is here. I got a tornado 1, tornado 2. So tornado 1's like, okay, you got a warning area that comes out. This warning area with the purple is actual rotation indicated, or somebody spotted something. And then you got tornado emergency. They'll put another purple square inside one of these boxes if it's an emergency, take cover right now. So not just saying if you're in one of these warning areas you shouldn't be prepared to take cover, or be close to your area that you're going to get into. That's, you need to be ready to get there in case something does happen. don't wait till the emergency where they're saying take cover right now and then get plowed with a tornado. Alright, let's get alright, let's see. I am going on 3 hours. Not trying to break any records. This is my record on Twitch, but it's weather. I can pretty much talk about this stuff all day. We can go to let me go national radar. You can still see that rotation. Snow wrapped around behind that. Let me refresh this thing. I want to make sure we got the latest data. All right, so no, we moved now. So you can definitely still see the comma signature on there, and that's why we're going to look at a satellite too. But we got some pretty significant snowfall through the Dakotas. Mixture on eastern South Dakota down into Nebraska, followed up by that thunderstorm. So now we get some, rain went through from that storm, and then now we got freezing rain on top of that, or snowfall on top of that. It's probably still a little bit warm there to determine if we're going to get any if they're going to get any ice or anything. We'll see what their temperatures are at. 28 degrees. They're cold enough. They're cold enough to obviously get the snow. Depending on what their temperatures were when that system went through. We are at, let's see, a couple stations in the middle of that low. 54 degrees, 60 degrees, 67 to the south, 37 to the north. That's our cold air mass, but that's pretty much, we can, it could have been warm enough today. How much accumulation they're going to get, it'd be a little bit hard to tell. I'd have to look at some charts on that too, but not real concerned with that right now. Nice little signature on the radar. Let's go to the satellite and look at that one real quick. Let's go. There's a loop. There's your significant comma shape frontal system. It's like the warm front's up to the north a little bit, pushing through. Cold front, cold occlusion. And you can see your snow on the back side of that low. This is true color on the daytime, and it's a multispectral IR at night, so it's infrared for nighttime. You'll never see visual during the day, at the nighttime, so they always got to go over to IR. And then they'll color that just to separate the kind of the low clouds from the high clouds. This brighter stuff is all your higher stuff. Now, if you look at these signatures, let's get a see if I can draw on this screen here. Go to. All right. If we look at this, we can pretty much look at the rotation and see our low pressure system. Watch that low. Makes a cold front. Cold occlusion coming out of there. It's a cold front. Looks like possibly a warm front. Now, high pressure is going to be possibly to the south. Let's look at our rotation here. We know we had onshore flow in the south. All this pushing in this direction. There's the ridge right there. If you look at basically a ridge right here, and then all this cirrus blowing over, spilling over that ridge, we know we got a ridge right there, so we could almost say high pressure there. High pressure here because of the clearing. Jet stream is going to follow always going to follow up behind that front. It will never cross over the front. It will cross through the triple point or to the north of the triple point with an occlusion. So there's your triple point. Let me clear this out. Go back low. Say, well, there's our front. Say an occlusion. And then our triple point would be right there. Now, a jet stream would push up, stay either right over that triple point or just north of that triple point and come around that warm front. It won't ever just cross over. You're just not going to have a jet stream just shoot over right across the front. They're going to kind of ride with these systems. That's why these systems are steer, to the northeast, because your jet stream is steering it. Your mid levels are steering it. We went into the upper levels. We've seen where our significant your steering flow was, so it went to the northeast. Now, so your jet stream, and then you have that ridge right there. So we did have like a jet max at the toward the south too. I think there's one over here. You can always get another finger of the jet in this area too. So you can have your polar front. Trying to find out where that went. I would almost have to drop down and back. So that was kind of like, I think it went like that. But if we have another jet finger to the south, then we could start to get the cutoff lows right around the four corners area. I'm going to clear this out. There's your four corners. You sometimes get a cutoff low and they'll just sit there. These systems, like this one, I think formed like over Colorado and just shot up to the northeast. That one system that went through Friday, that thing kind of formed down here and then just, what it was, a deep trough at 500 millibars. I mean, it was like this. Now, that overshot created a low pressure system, and then that just ejected from that trough and followed that jet stream right on up, and it was like, didn't even, there wasn't nothing slowing that down because it happened over here on the lee side of the Rockies. So that, if you get a cutoff low in the southwest, they'll just sit there. You'll have a jet max around that low. The main polar front jet will be to the north, and then this low would just sit here and sit there for several days and just rotate and fill from the bottom up and just dissipate out. Now, then your jet stream will be to the north. Because what causes your jet stream is your north-south temperature gradient. So if you have a high pressure system, clear that out. Go high pressure system. We're just doing this for education, not over this right now, but we did have a high over here. But now you got the high pressure system, leading edge of that air mass is your cold front we got right here. So now you have that high pressure system right there on the surface. The temperature change between the leading edge of that air mass and the leading edge of this air mass, the backside of this air mass, that warm sector, this is where your jet stream is going to be. That's your transition between your cold air and your warm air. Now you got your jet stream. Thermal gradient, north-south temperature gradient is what's going to cause the jet. So, got a warm sector, cold sector, got your warm front, that's supposed to be red, got your cold front. So your jet stream is going to basically stay right behind your cold front, right where that transition is, where that low pressure, stay in the trough, and then shoot up over that ridge. Now, you can get conveyor belts. I mean, there's so much into this, with all this dry air that pumps in to these systems. You can get moisture just continue to pump in. You can just sit there and watch like convection pop up in one area, move out, just from the winds. It gets up into the upper levels and the winds shears it off, and then just keep building in that one area and shear off, and building that one area and shear off. If you can get that from those conveyor belts just push that moisture in. And then you got the lift, the instability and the lift in that one section, and then every time it gets up into the upper levels, it just pushes into the, it just blows off from the upper level winds. Now, the closer the jet stream is to the surface, like we were talking about earlier, 850 millibars, you push 45 knots down close to the surface at 5,000 feet, then you got your exhaust. So if you have a tube, let me get out of this. Erase that. Now, if you have a tube, a column of air, and you blow air over that column of air, it creates a suction, and it can suck that air mass, suck the air right out of that column. So if you have that low pressure system on the surface, now you have mass just being sucked out by the jet stream, blowing air right over that column, that low, and then this low is just going to intensify and become what basically kind of what we have. But that's not happening of what we have right now. We have a pretty significant trough with thermal advection support as our upper level support. We do have the jet support. We do have the low on the surface. I mean, we do have that jet support to help with that upper level divergence. So, all right, let's go back, look at something here. Let's see if I can get back to a chart. I'm going to see what let me get my station plots cranked up. Let me go to 300 millibar. We're going to 30,000 feet. And I'm going to do the balance height for now. Actually, I don't even have to do that. Let me go. I don't want to do the height on this. It takes a minute, but let's wait till that gets done now. I don't want to, if I interrupt it, it'll take even longer. So I'm going to pull up the jet stream, and I'm going to pull up the station plots that we had. Alright, I'm going to take a break for just a second. My girl's going to bed, and I'm going to say goodnight. So hold on just a minute. Alright, I'm back already. So, here's our jet stream. I want to get our station plots on here because I want to see what we can do for convergence or divergence. Now, it's be pretty interesting if we did this. Let's go to the surface and put our surface pressure on a 30,000 millibar chart. Now what we can do here is pinpoint our center low. If it comes up. Okay, there it goes. Alright, so here's our low. Remember, this is, you'll never see a chart like this. Come on. Alright. There's our surface low. I don't have any data up for upper level troughing or anything like that. But what we're looking at is here's winds going in over that low. Here are the winds coming out of that low. So then we got our jet stream ridging right there over top of that low. And then our jet maxes are always over there off to the northwest. So if we went up to, we got a little bit of a jet max right there, there's a yellow. But if we went up to 250, then we'd probably see a little bit more color in that area because there's our strongest winds. So right there, 70 knots, 70, 75. Looks like here's 120. Here's 125. All right, so now going into the low, 65, it looks like 65 knots. Coming out of the low, 120. So now what do we have? We got a heck of a difference there. So we're looking at divergence because we got more going out than what's coming in. So we have upper level divergence, speed divergence. So any mass that hits over top of this, there's nothing going to build up right here. It's going to be sucked out. So now we have upper level divergence and creating that low to even get deeper. So we got 997 millibar low. It should be deepening because of this divergence. Now another one is that's speed divergence. Another one is it's not a whole lot of data in Minnesota. I'm at 99% on my plot, so I just don't see it. There must not be a lot of balloons let go, or they just didn't launch one because of the incoming weather or whatever. But so another one would be winds travel in that direction. That direction. Alright, hold on just a minute. I'll be right back. Okay, that was real that time. She said good night, so can't pass the girl up telling her good night. Anyway, we got wind direction going through that low, wind direction coming out of that low, wind direction. And then we got a shift there, but we're not really concerned about that. We're just looking at, what we're kind of looking for is, we got this one going through here. So we keep that straight line. This one keeps that straight line. We can see right there is actually a pretty good example. So there's that wind. Here's that wind. Now we have the winds are going away from each other. So we have upper level divergence in that area. So now that's another indicator for directional divergence. So we get directional divergence, we got speed divergence. So when the jet stream, so we got upper level support to continue to pull mass out of that low and cause that low to go deeper. Now, high pressure dominates low pressure all the time, and all the winds flow out of a high, clockwise around a high, and out of a high. So counterclockwise around the low and into a low. So your high pressure is always, your pressure is always flowing from high to low pressure. So it's always trying to constantly fill that low. But if you have the jet stream keep sucking that mass out, no matter how much the high pressure is pushing into that low, it can't fill it fast enough to, keep that jet stream from pulling it out. So that's just you can get those indicators by your upper level divergence and what this low pressure is going to do. It looks like it's it's pretty intense right now. I mean, these contours, you're pulling 100 and what's that, 25, 30 knot winds right there. That's pretty significant wind flow. Okay. I think we're about done. I'm going to, like I said, I got the 12Z data. I don't know if I've even, when I downloaded this, if this is the updated data for the, let me go see here. I don't know if that's going to tell me 0Z Thursday the 16th on the sea level pressure. So my surface is correct, and I'm at 12 to 14. It's at 1150 to 14 Z. The station plots. That's on Thursday the 16th too. So that those upper level charts might be updated now. I don't know why I can't update that sounding. So I didn't get the sounding data. I'm just gonna go look at let's go in Ohio. Look at the sounding over there. What are we at? 12Z. We're still 15 December 12Z. We had some pretty thick clouds today, and then we obviously had that inversion. We had a big dry area from the surface up to just over 5,000-6,000 feet. That's when it all started, and then we got a dry area above that, and then it got pretty moist in the upper levels too. So I was going to pull the 0Z data. I might come back in a little while. Let's see what we got here. Let's go back to the radar real quick and double check on our storms. What we got here? We got another train spotter reported a funnel cloud in that area. Alright, so warning after warning. They're not holding back on the warnings. Which, hey, if you got rotation according to radar, then that's a good reason to set your warnings. Get rid of them thunderstorms. So this is pretty much heading almost northerly now, and that should be I think the significant weather, the heaviest rainfall was going to be wrapped around that low, and that was going to be in northeast Minnesota. So they're going to get some warnings set probably in Wisconsin. If I had the soundings, to go pull the air mass and see what kind of cape we have, and to look at the instability indices and see where all that stands. But I would definitely say they'll continue with the warnings there, just because the intensity of this low pressure system it's pretty wrapped up. So there's really nothing there. We've seen the upper level divergence on the charts. Nothing really slowing this low pressure system down a whole lot. They'll go up over the Great Lakes, probably pick up some more moisture, and bring some significant, maybe some lake effect snow or some snowfall in that area. So once we get down in the areas where that freezing level is. Actually, one other thing on that thickness chart. I don't know if I can build on it real quick. Actually, I'll put the thickness lines on here. Get out of that.